Okay, everyone, welcome to day 2. I hope you all had a good first evening. Today, we've got a slight change to the schedule. Instead of Matt giving a tutorial on temperature, timing, and jug, and a kind of PTA timing software today, we're going to move that to Thursday. And then today, we'll have an extended kind of kickoff of the mini projects in the afternoon. So after lunch is pretty much free hack time or just your free time. I'll point out different areas that you all can meet up in that are different from this room as well. And if you're unsure of how to get started, just talk to me or one of the organizers, and we'll try to kind of nudge you in the right direction, something that might interest you. But first of all, before our first lecture of the day, Sebastian is going to give us an overview of the research he's been doing and his interests. This is kind of inspiration for you all to do the same thing. We've had a few signups for these morning pre-lecture talks from students at the summer school. So it'd be really nice if you all could think about doing the same thing. There's no requirement to do it, but let people know what you're up to and what your interests are. So Sebastian, kick us off. Let's get around.
Thank you, guys. Oh, is there, what, can I?
What do you need?
The Google slides, not bad, the research slides, yeah. Should be in the Slack, link should be in the Slack that me and Lucas sent, going back.
There's no Slack on this.
Oh, okay.
Want to bring up your computer
Yeah,
and
yeah,
just share screen?
Yeah. Latest. No, I just hooked it up to the laptop. I plugged it in here. Oh, perfect. This is why Lucas said I'm the sacrificial lamb, by the way, figuring this all out. Beautiful. Okay. By the way, I copied these slides from a recent conference. That's why they look kind of prepared. Your slides do not have to look like this. Any overviews is more than enough. But yeah, I work on detecting supermassive black hole binaries with light, particularly looking at optical variability of active galactic nuclei as a way to detect supermassive black hole binaries. Okay, so just for a brief review, I know most of you guys know this already, but supermassive black hole binaries form following galaxy mergers. And following the merger, a series of dissipated processes will drive the two supermassive black holes towards the center of the common merger remnant until they eventually approach each other close enough to form a gravitationally bound binary. Now, after reaching roughly milliparsec separations, they'll begin emitting gravitational waves that are detectable by pulsar timing arrays. These gravitational waves offer us an avenue to directly detect the binary and to probe the binary's dynamics, which is very, very useful information. It would also be extremely useful to get an electromagnetic counterpart of these binaries, because that would allow us to study the binary's outflows in its local environment, which allows us to make a lot more conclusions about the relationship between these objects and their host galaxies, and probe a bunch of other interesting accretion and relativistic theories. So that is to say, my research focuses on acquiring those electromagnetic counterparts. Now, the problem is that even if these objects form in gaseous environments, right, when these two supermassive black holes would be accreting gas and shining very brightly, they would each look like an active galactic nucleus, okay? And this has been detected, going back to the last slide, as dual AGN, right? These objects have been found before, two supermassive black holes that are actively accreting in the same galaxy. Typically, they're found on roughly kiloparsec level separations, but they've been detected as close as 7 parsec, okay? But the problem that's demonstrated in this little silly graphic is that if you bring these two AGN that are shining very brightly and that are very distant, very far from us, if you bring them very close at milliparsec level separations, their point spread functions begin to overlap and they just look like another AGN. They just look like a single AGN. So in a single photometric snapshot, it's impossible to distinguish a single supermassive black hole from a binary of supermassive black holes. So instead of looking at a single photometric snapshot, we monitor these objects' variability. That is, we look at AGN light curves and look for a signature of binarity. Specifically, this signature is, at least in this project, we assumed this signature is a sinusoidal modulation in the object's brightness. There's a lot of reasons why an AGN or a binary's light curve would modulate periodically. In this research, we assume it's due to relativistic Doppler boosting. I can get into more of that later if anybody has questions. But overall, to distinguish a single supermassive black hole from a binary using optical variability, we need a period finder to look at these light curves and be able to detect a periodic signal. And that's what I work on. I reviewed 3 methods on 3 different types of light curves in the recent paper I published. I'll be going over just 2 of the methods for brevity and for interest. The first method that I looked at was Lohm-Skargel periodograms, generalized Lohm-Skargel periodograms. I'll just be calling these periodograms in the future. All they do is fit a sinusoid at a bunch of trial frequencies. Okay, so it's just searching for a raw sinusoid in your data, and that's it. Okay. The process of getting a periodogram itself is very, very quick, but to make sure that we're resistant against classifying non-periodic light curves as having a periodic signal, we also have to gauge the false alarm probability, okay? Roughly speaking, the false alarm probability is the probability that a non-periodic light curve can trick our periodograms into thinking that we found a periodic signal. And the process for computing this takes a very long time, okay? It takes roughly an hour. It takes roughly an hour per light curve, which kind of washes out the computational benefit of using periodograms in the first place. Okay, if it takes an hour to analyze each light curve, then the computational efficiency afforded to us by using a frequentist method is kind of lost. But nonetheless, this is the procedure that we use. And the false alarm probability, we calculate it by just simulating a bunch of noise-only light curves without a periodic signal, feeding them to the periodogram, and basically gauging how often do these noise-only light curves generate a detection. How often do they generate a significant periodogram peak? Okay. Yes. The next method that we use is a nested sampler. Just like any sampler, it's going to fit some arbitrary model to your data by sampling over some parameter space. Unlike MCMC sampling, though, it doesn't just drop a bunch of walkers into a parameter space that individually explore the likelihood. It kind of maps out the entire parameter space and slowly pairs down until it's found the most likely parameter matches, the best fit parameters that make your model fit your data. This is very useful to us. As you can see, a little demonstration of what I just said right here. We have the parameter space, the nested samplers mapping out the entire parameter space and slowly pairing down until it isolates the best fit parameters. This is very nice because by mapping the entire parameter space, the nested sampler can produce an estimate of the marginal evidence for each model. Okay, this is kind of like a rating of fitness for each model. This is something that the MCMC has a very hard time gauging, but the nested sampler provides it to us. And by getting this rating of fitness, we can fit 2 different models to our light curve. We can fit a model that only contains the intrinsic AGN variability, that we expect from a single AGN, and we can fit a model that corresponds to the binary case, which is that variability plus a sinusoidal signal. Okay. By fitting both of those models, we can then compare the rating of fitness, the evidence, Z, and take the difference to be some indication of evidence for periodicity. Right? We take that as an indication of evidence for binarity. Okay. So with these two methods, we simulate a bunch of light curves, a bunch of Rubin-like light curves in this paper, and we feed them all to the periodograms and to the nested sampler. Each light curve will then receive from the periodograms a false alarm probability, and from the nested sampler, a delta Z, a difference in evidence. And then we use those difference in evidences and those false alarm probabilities to perform binary model selection. That is to say, if the FAP or the delta Z is low enough, then we classify the light curve as a binary. If it's too high, then we classify it as a single AGN, okay? An ROC curve is a tool that we use to say, okay, based on, or if we try different thresholds for the FAP or for the delta Z, what does our model selection look like? How many true positives do we classify? How many false positives does our classification scheme produce? Okay, and by scanning through different values of the FAP and the delta Z to use for this, we can get a sense of how robust each classification scheme is. Okay, what we've done here is plot the ROC curve, roughly speaking, for the nested sampler in purple and for the periodograms in the dotted or the dashed yellow line. And overall, they're very similar, which is significant because the nested sampler, just in a straight test, takes a very, very long time. At least at the time of doing this, it took anywhere from 2 to 20 hours to run per light curve, so very inefficient. Whereas the periodograms, like I say, were much more baseline efficient, roughly an hour per light curve. And yes, yeah. But because in the problem of looking for a binary signature in AGN light curves, we have to face the reality that we expect single AGN to outnumber binary AGN at least 1,000 to 1, roughly speaking. We care a lot about reducing the false positive rate. Whatever our classification scheme is, it would be very nice if we capture as many binaries as possible. But because we're expecting tens of millions of AGN light curves and maybe only tens of thousands of binaries, we are most interested in minimizing the false positive rate. Okay, so we're going to take a closer look at this range of the ROC curve. And when we zoom in, we can see that the nested sampler is much better. Okay. For the same false positive rate, which is roughly 0.5% as indicated by those stars, the nested sampler gets about 10% more true positives, which is a big difference in this case. Okay. This is an interesting result, but nonetheless, you know, these are test light curves, so take it with a grain of salt. But overall, in a general test, we can see that if we use the delta Z cutoff of -9, the FAP cutoff of a 4 sigma detection, we get these false positive and true positive rates indicated on the left-hand side, 0.3%, 51%, so on and so forth. Using those cutoffs, we can see basically how our classification schemes detect light curves with different intrinsic properties, okay, because we simulated them. On the left-hand side, I've plotted the detection rate, or you can think of it like a true positive rate. The detection rate versus an amplitude ratio, which takes the ratio of the sinusoidal amplitude to the damper random walk amplitude, which is the intrinsic noise amplitude. Okay, so the higher this is, the more noticeable the periodic signal is. And as you'd expect, as we increase that value, our detection rate goes up quite a bit. But for the entire spectrum of light curves, the nested sampler detects more of the light curves than the periodograms. On the other hand, if we look at the injected period of the sinusoid, as that period increases, both of our methods, their performance decreases. They do a lot worse detecting periods that are comparable to the baseline of our observations, which is 10 years. This is overall expected, but it is still notable that we managed to detect about 40% of the light curves using the nested sampler when their period is 10 years long. Okay, it's a very difficult task to detect a periodic signal if you never see it repeat, but that's what we're doing here with the nested sampler. Okay, but overall, the things to note is that we need an amplitude ratio of roughly 2 to get a significant true positive rate, at least 50%. But yes, this is kind of a interesting result as well. One thing that I didn't mention in the interest of time, but I'm just gonna, hopefully you take it for granted. One of the problems I mentioned with the periodograms is that to compute the false alarm probability, to classify these light curves, you're basically losing out on the computational efficiency that a frequentist method affords you. We look into an interesting way to circumvent that long calculation, to circumvent that hour-long FAP calculation, and instead amortize the cost of that FAP calculation, do a bunch of preliminary computing, and use those values to basically instantly calculate the FAP for all the light curves that you analyze with the periodograms. I can talk much more about this if you're interested. Like I say, take it for granted now. But using this abbreviated procedure, we plotted the ROC curve that we get using those approximate false alarm probabilities in the gray. And we plot the yellow, I'm sorry, we plot the FAP values or the classification for the FAP values the correct way in yellow. And you can see that using this abbreviated procedure, we very, very closely replicate our initial results, okay? Obviously, it's worse. We can see that from the plot, and just from looking at the gray curve gets slightly worse true positive rates. But nonetheless, it's very impressive how close these ROC curves are, considering that the abbreviated procedure takes roughly 20 milliseconds per light curve, okay? Whereas the periodograms with the full procedure or the nested sampler would take millions of hours to analyze all the light curves coming from Rubin. This abbreviated procedure would allow us to analyze that entire volume in less than a week, okay? So interesting procedure. But yeah, that's the main findings of this recent work. Overall, the nested sampler was better than the periodograms, but it took much longer. The periodograms were okay, a little bit underwhelming, but when we look at this triage procedure, this abbreviated procedure, we get some interesting results. We get some intriguing results that could be investigated further as a way to handle the huge incoming volume of Rubin light curves. And then just for an update, I've been working on simulating multi-band AGN light curves. Yeah, testing new samplers that can handle this complicated data stream. But if anyone's interested in talking about this stuff, I'm also happy to discuss it. But yeah, that's all I've got today. So thank you for listening.
The other samplers that you need prior.
Using all nested sampling, so the same ultra nest sampler. And this is because when we're looking at binary versus AGN light curves, it's very, very nice to be able to tell which model fits better, the one with a periodic signal or the one without a periodic signal. So, you know, it's a little bit difficult to try things like MCMC samplers, even though they are much, much faster. But entirely nested samplers, you do need to make some modifications to allow it to handle multiple bands of AGN light curves at the same time. But that's what I'm trying out right now. Yeah. The intrinsic AGN variability has two parameters, an amplitude and a time scale. It's called the damp random walk. And then the additional parameters for the periodic signal are an amplitude of the sinusoid, the period, and the phase. That's it.
There's or other non periodic but non.
Yep, we completely ignore that in this paper. This is a paper I started in my RU, so it was very simplistic assumptions. As you can see in these light curves in the top left, though, we're beginning to incorporate self-lensing with the help of Tejas. Self-lensing flares accretion rate variability. All those signals are non-sinusoidal and they can become extremely, extremely difficult to extract. Eccentricity, yeah. Yeah, there are a lot of parameters that make the periodicity much, much more complicated than a sinusoid. This is a good proof of concept. And as you pointed out, those are non-sinusoidal. So something like a periodogram would probably not be very useful for that at all. Tejas.
What allows the nested and impact the item for MTMC
Mhm.
for school populating the area region?
We're populating the posterior distribution, yes, but the nested sampler is forcing it's being forced to map out the entire parameter space. So it begins by defining a grid over the entire prior space that you've given it, the entire prior volume you've given it. And it quickly moves away from regions with low likelihood, but it still forces samples in those regions. Whereas the MCMC sampler just follows a random walk tending towards higher likelihood. So it misses out on large volumes. That's a rough explanation. I'm sure Steve can give you a better one.
Maybe you'll hear more about this later.
Sounds good. But the simplest way I can think about it is if you drop a bunch of hikers onto a mountain range in the dark, MCMC is like if they all start wandering around and trying to find a peak, just stepping towards the highest altitude step they can find. Nested sampling is if you box in that entire mountain range and begin filling it up with water until you keep on filling it up and slowly isolating the peak. That's kind of how nested sampling goes. Yes.
If we put in multiple walkers, does that change anything, or is it still big?
It's a good question. I don't have a bunch of experience with MCMC, but my understanding is that it's kind of diminishing returns. The more walkers you put in, the more computationally expensive it becomes, and you're not getting a bunch of new parameter space. But I'm not sure. Mhm. Anybody else? Yes. Mhm. Okay. Mhm.
Help me make sense of the timescales that are implied by, I guess, the sinusoidal signatures that you're looking for. I think I was under the assumption that, because you're seeing that much periodicity and restricted amount of time, I would think of that as like being close to merger.
Mm.
And so it's never clear to me how one can trust any kind of sinusoidal signature in a VIPER if we know that the timescales of probing are such that, it's near merger. So it's like, how you.
Mm. Yeah, that's a good question. It's a subtle question. Because overall the periods that we inject, that we test range from 30 days to 10 years. Okay. And depending on the mass of the binary, binaries with those periods have long time to mergers, right? They might still be in the inspiraling phase and they will merge in tens of thousands of years. And it's a calculation you can carry out with the mass and the period, pretty straightforward with assumptions. But for the specific case of this sinusoidal modulation, I mentioned relativistic Doppler boosting, okay? And with relativistic Doppler boosting, we're assuming a circular orbit, and we're assuming that most of the gas is accreting onto one of the black holes, the secondary black hole. And we say that, okay, that a little disk formed around this secondary black hole will periodically brighten and dim as it moves around in its orbit, right? As it periodically approaches and recedes from us, its apparent brightness will increase and decrease sinusoidally. But I did forget where I was going with that. Can you ask the last part of your question again? You said the.
Timescale because, maybe I was naive, but I was under the assumption that with such short orbital timescales, that I guess the changes wouldn't last very long because we're very close to merger, and so it's. I kind of tend to think of the sinusoidal signatures and VIPERs as very momentary, that they're probably not gonna last long even if you supposedly have them. And so it's just the timescale stuff that always throws me off.
Yeah, what were you thinking?
You mean close merger? I mean, close merger is the relative mass dependent definition, right? Because if you have like supermassive black holes, massive black holes, the close merger part can be several thousand millions of years depending on what it is. So in 10 years, those things, I think they're more being monochromatic, even if they are drifting.
Mhm.
I wouldn't say that, but you should have. I would say the measure time scale is comparable. So I would be probably thinking maybe you have like 10 to the 6 and above the masters of PTA, and because there's roughly same mass ratio, I would tend to think that the time scale is big enough that you see those kind of on that. So time will probably, but it's a matter of calculation.
Yeah, I agree. I think the merger timescale is less of a concern. I'm not sure if this was what you were getting at, maybe, but the timescale over which the periodic modulation is consistent, that's definitely up for debate. We don't have any consensus on that. We've seen quasi-periodic oscillations where a signature repeats 4 times and then it stops. We don't know what that is. That could be something like relativistic Doppler boosting, but then something happens to the accretion disk that disrupts it from being visible, even though there's still binary orbital motion. We don't know. But like you say, the merger timescale is less uncertain. The timescale of the signature is definitely up for debate. But yeah, we can talk more about it later.
More will be revealed when Chesney gets word.
Yes.
Tomorrow than the very
Yeah.
That's next slide. Okay, so that's how it's done. If you did want to take a presentation you've given before and slim it down a little bit and kind of recycle it for this kind of purpose, you're very welcome. If you're preferring not to give this kind of research presentation in the morning, that's fine as well. So we'll move on to the first lecture of the day, and that's Professor Cromartie. Frank is our new faculty member here at Vanderbilt. He is one of the world's foremost experts on pulsars and theory of pulsar-timing and practice of pulsar-timing. Has led so much in nanograph collaboration and is still the chair of the Timing Working Group. So Daniel is going to tell you all about pulsars and so well. Thank you. Just connect via this.
Oh, right. What am I doing? Oh, still, I'm already on the Zoom.
Yeah, I think that's what we need. If you did want a pointer.
Thank you. I appreciate it. How are we doing here? Okay. Cool. Let's go ahead and get started. Thank you so much, Steve, for that very flattering introduction. I really appreciate it. And I'm really glad to be with all of you here. So as Steve already said, we're going to talk today about pulsars, which are sort of our the key component of a pulsar timing array, as you might imagine. And we're going to talk about how we time them to very, very high precision and sort of in doing that, how we can detect gravitational waves, though I'm not going to really touch on PTAs themselves because Steve is going to talk about that a little bit more later. Okay, so we'll start out just very basic with the astrophysics. We'll talk about pulsars as objects in and of themselves rather than just clocks that we can look at. So as you likely know, the fate of stars is completely dependent on their mass, right? So if you have sort of, a progenitor star that's less than about 8 solar masses, you're going to end up with a white dwarf. If you have something that's way, way bigger, something like 10 to 30 solar masses, it's going to collapse into a black hole. But if you're in this sweet spot, more than about 8 solar masses, and it's not totally clear where the line between the neutron star and black hole progenitor is, but if you're in that area, then you have a star that's going to be fusing elements all the way up through iron, right? And so, as it goes and goes and goes, it's producing energy that's protecting against gravitational collapse. But by the time you get up to iron, you're not producing enough energy in order to protect against that collapse. And so then you have a core collapse supernova that turns into a neutron star. And so neutron stars are sort of the star of the show, as you might say, today. These were actually predicted very, very early on, right after the discovery of the neutron. So Bada and Zwicky in 1934 were already able to predict that a neutron star should exist, despite them being very exotic, very strange objects. So these are balls of neutrons. Basically, that's a gross simplification. We'll talk a little bit more in detail, that are supported by neutron degeneracy pressure. It can sort of be likened to how white dwarfs are protected against collapse from electron degeneracy pressure. And what you end up having is this extraordinarily dense object. So if you want kind of a real world example, if you had a paper clip that had the density of a neutron star, it would weigh as much as Mount Everest. So these are densities that are several times nuclear saturation, the sort of density of atomic nuclei. And this is very unintuitive. It's pretty amazing that objects like this can exist. We know that neutron stars in general have radii of something like 10 kilometers in radius and something like 1.4 solar masses and above. We're going to talk a lot more about the sort of masses and sizes of neutron stars later, though. So that's just a very basic canonical neutron star. So pulsars, the discovery of pulsars was pretty amazing. It's a great story. I'm sure many of you know it already, but I'm going to repeat it. I'm sorry. So there was a graduate student at Cambridge, Dr. Jocelyn Bell-Burnell. She was doing an unrelated project with a very low frequency radio telescope, not looking for neutron stars, not doing anything like that. But with time, she was analyzing the strip chart recorder, so just the output of this radio telescope. And she started seeing this scruff. So it would have the same sort of periodicity and come at the same time every day. And she started to think that maybe this isn't just instrumental interference. It really was too regular to be something that wasn't, astrophysical, and coming once a day is certainly a sign of that as well. And so she identified the first pulsar, and they called them LGM initially. This was like sort of a joke, sort of not a joke, for little green men, because these signals were so periodic that they really did look like they were of human origin. They were not aliens. They were actually pulses from a pulsar, which are spinning neutron stars. And I also wanted to point out, so, I like to mention, at least briefly, that Dr. Bell-Burnell was snubbed by the Nobel Committee in favor of her advisor and her department head. You can read her account at that link. She has never sort of harbored any ill will due to that, but I think it is good to mention. And I think this is a really interesting sort of cautionary tale as well, right? So this is a quote from this textbook called Essential Radio Astronomy. And it's sort of telling you that one of the lessons that you can learn, other than, sort of being very tenacious, really sticking with your gut, believing interesting things you see, is that you really should be aware of over-processing your data and not understanding your instrument. Right? So we have a lot of algorithms, we have a lot of complicated sort of data cleaning methods, things like that. But if any of this had been sort of automatically cleaned up, the pulsar signal almost certainly wouldn't have come through. And in fact, we know that some very bright pulsars were seen in previous data sets, right? So pulsars could have been discovered significantly earlier. But in reality, it took Dr. Bell-Burnell's sort of very careful, very intimate knowledge of the instrument, as well as her very careful inspection of the data and understanding what was normal and what was not normal in order to actually get out the signal or identify the signal as something astrophysical. So I have a cute little video of a pulsar. So pulsars can be likened to lighthouses. They are neutron stars, as we've already said, that have these very strong magnetic fields. They beam radiation out of their magnetic fields as they spin. And so they're sort of like a lighthouse. They're not actually pulsing. They're just rotating. So when the beam crosses your line of sight, you see that as a single pulsation. But in reality, it's just a lighthouse. Pulsars are really cool because we can use them as clocks. They have these very stable pulse periods, though some pulsars have more stable pulse periods than others. You can also, if you just want to do some very initial calculations to try to figure out some basic properties of the neutron star, the observation of pulsars lets you do that. So if you have, for example, the period of the pulsar, you can set the condition that centrifugal acceleration at the equator, this pulsar isn't ripping apart, right? So it can't exceed the gravitational acceleration. And if you go through this calculation, this very basic algebra, you can see that if we have a pulsar that's like 1.4 milliseconds in its period, so spinning quite fast, then the density that's implied, the average density, so this isn't even a maximum, is as dense as an atomic nucleus. So this was very startling. I mean, it was sort of predicted, but it's still kind of amazing to see borne out experimentally. I'm not going to talk very much about pulsar emission mechanisms. The pulsar emission mechanism is not super well understood. There are some nice toy models that we can talk about, but we're not going to get into really, really super specific, a deep dive into the emission mechanism. But you can sort of, the initial star prior to collapse has this approximately dipolar magnetic field. And so when that core collapse supernova does happen, you're shrinking the size considerably. And so, the magnetic field that you get as a result, and also the rotation, are very extreme. So pulsars actually have, they can have magnetic fields up to 10 to the 15 Gauss. A more typical value would be something like 10 to the 12 Gauss. But if you compare that to what the Earth has at half a Gauss, it's very, very startling. So these are really neat objects. They can be approximated as rotating magnetic dipoles. So you have this misaligned sort of magnetic and rotational axis. As the pulsar rotates over long periods of time, it's going to spin down, it loses energy. And this is like a very basic sort of view of the situation. But you can think of this as a rotating dipole that's losing energy over time. So if you do assume this dipole model, and you measure the period and the spin down of the pulsar, you can calculate some very basic properties. We won't go through these calculations, but I'm happy to show them to you. You can calculate the luminosity that's implied by its spin down. You can calculate the actual strength of the magnetic field, and also the implied age of the pulsar because it's spin down. So this is the one emission mechanism thing. So the very basic picture here is that these strong magnetic fields are inducing an electric field that pulls charge out of the surface of the neutron star, and it creates this sort of shielding, this magnetosphere that's co-rotating with the neutron star. So they're sort of stuck together. But you can imagine if you get far enough away, because this is, sort of this co-rotation is happening, if you get out far enough, you get to a point where the magnetic field lines can't reconnect anymore, right? So you've gone out too far. Everything you see sort of with these connected dipolar magnetic field lines is sort of safe. But then when you get out to enough of a distance away from the rotational axis, you start having magnetic field lines that can't reconnect. And so this is sort of the origin of the pulsar emission. There are electrons being pulled out that are emitting curvature radiation. There are these particle cascades that are happening. There's a lot of complication brought about by the fact that, you can observe pulsars at different frequencies, but the origin of the emission is not necessarily the same for every single frequency, right? And even for just the radio emission, the sort of height above the neutron star surface at which that radiation is being emitted varies as a function of radio frequency even. So it's a very complicated picture. We don't need to get into it too much more, I don't think, but that's kind of a very basic view of it. So you have this magnetic axis, radiation's going along it, and it's a lighthouse, and then you're good to go. So there are these very specific, very special sort of objects that are part of the pulsar population, and these are millisecond pulsars. So for the rest of the talk, we're mostly going to be talking about millisecond pulsars. These are the ones that are most interesting to us in the context of pulsar timing arrays. These have companions, and they've accreted matter from the companion, and just due to conservation of angular momentum, they've been spun up to these very fast accretion or fast rotational rates due to accreting that material. And so during that process, which we call recycling, the magnetic field is actually shielded somewhat, and so these millisecond pulsars have weaker magnetic fields for sure. But they, you often end up having this sort of white dwarf companion in orbit with a pulsar, and that is kind of the most canonical system when you're thinking about pulsar timing arrays. The vast majority of millisecond pulsars are found in binaries. For the ones that aren't, either they've ablated away their companion or the companion's been kicked out of the system during the supernova process. And the other thing that happens during this recycling process is that the orbit is made very circular. So the accretion process really stabilizes the orbit, and it creates these orbits that are kind of unbelievably circular, to be honest. And that makes them really fantastic for pulsar timing, which we're going to talk about in a second. So this is one way of kind of visualizing the population of pulsars. This is a period derivative versus spin period diagram. You also have lines of magnetic field strength going from low magnetic field strength to high. And you can see that, pulsars, when they're first born, are very energetic, but they aren't very stable. So they're losing energy quickly. They're much harder to time. They're very volatile sorts of sources. But as these binaries, at least, go through the process of recycling, they find themselves in this bottom left corner. So these on the bottom left are the fully recycled orbits, fully recycled binaries. They have really low eccentricity. They're very stable, so the pulsar doesn't spin down very fast with time. Its magnetic field is a lot less strong, so it's losing less energy, and they spin extremely fast because they have been spun up to those really crazy fast rotational rates. So when we're talking about timing pulsars, this is where the order of operations gets a little bit awkward. But I do want to talk about why the interstellar medium is really important for us to think about when we're talking about pulsar observations. So as the radio emission is crossing the galaxy from pulsars to us, right? Most pulsars, the vast majority of pulsars are quite nearby, definitely galactic. There are some found in globular clusters, but we're not really observing pulsars in other galaxies, for example. So on their way to us, they're passing through this plasma, this like very inhomogeneous, kind of like turbulent, changing very quickly with time, interstellar medium. That's all I wanted to say, interstellar medium. So as it passes through, the pulses are dispersed. So that is this 1 over radio frequency squared relationship that you see in the plot on the left. We'll talk a little bit more in depth about DM on the next slide. They're also, the pulses are subject to diffractive and refractive scintillation. These cause flux density changes. So sometimes you can have a pulsar that's scintillated down very extremely, even to the point where it can't be seen anymore. And then you also have scattering, which is pulse broadening from multipath propagation. This is way stronger at low frequencies. And so you can see one theme of this is that when you're observing at low radio frequencies, you really are subject to these kinds of uncertainties due to the interstellar medium, which can be a real source of uncertainty in pulsar timing array experiments. So we don't need to go through the derivation. The only real thing I want to tell you about dispersion measure is that it's proportional to the observing frequency, 1 over the observing frequency squared. So it's much worse for low frequency data in the radio. And the other thing is to think of dispersion measure as sort of the integrated column density of electrons along the line of sight where you're looking. Dispersion measure is really interesting because you can actually use it to estimate distances. So there are maps of the galactic electron density. And so you know that if you are looking through a certain amount of material towards a certain known structure, towards something that has been looked at other frequencies, then you are going to expect a certain dispersion measure. And so that, in addition to measuring things like parallax of the pulsar, are two of the ways we can estimate distances. But these electron density maps are not very exact. They don't give us high precision distances. They give us a sense of what the distance might be to something like 30%. So it's helpful, but it's not, super, super precise. Oh, and this is just a little cartoon of the same thing you saw on the last slide, right? The low frequencies. If you integrate over this multi-frequency data, like you see on the top, you won't actually bring out a pulse, right? So you have to de-disperse your data. You have to bring all of those frequencies into alignment in order to, when you actually integrate, see the pulse itself. And so if you're not de-dispersing your data properly, it's very unlikely, unless you're not off by too much, it's unlikely that you would even see a pulse from a pulsar. So how do we actually observe these things? Most pulsars are not like Dr. Bell Burnell's initial pulsar, right? Or even the bright few pulsars that were discovered after that. Especially millisecond pulsars, we're talking about pulling out this periodic signal from a sea of other signal, right? So it's this very difficult problem. It's this very weak sort of signal, but it is periodic. And that's the reason why we can study it very well. So pulsars are very steep spectrum emitters. They emit at low radio frequencies, a lot more than they do at higher radio frequencies. There's very little emission in sort of the middle of the electromagnetic spectrum. In the optical, infrared, everything, pulsars aren't doing much. You can look at the nebulae that they might reside in, but the pulsars themselves are not great for getting studied there. Their companions sometimes are, though, which can be quite helpful. The best sort of instrument to study pulsars in the radio turn out to be large single dish radio telescopes. So that's a little bit interesting because there are a lot of radio astronomy applications that don't really favor these single dish radio telescopes, right? But pulsars don't need to be resolved. They're point-like objects. And so the only thing we really care about is increasing sensitivity by increasing our collecting area. And so a single dish radio telescope is a pretty good way to do that. So you can see some examples of the ones that we use for various pulsar timing applications. These are just like randomly selected. You can see Arecibo in the top left from Contact. And then you can see the GBT, Parks. These are all sort of like 50 to 100 meter class radio telescopes. Arecibo was 300 meters. It was a really amazing instrument. In China, there's the FAST telescope, which is a 500 meter diameter. That is amazing. They have found so many pulsars and they're able to do very precise pulsar timing because they have those capabilities, because they have this giant light bucket. So observations in the radio are usually between, sort of the couple hundred megahertz to a few gigahertz range. But there are lots of exceptions. There are people who work on low frequency observations, so less than 100 megahertz. There are people who look at pulsars, and it's only some pulsars because many of them do have that steep spectrum. But you can look at pulsars at higher radio frequencies as well. I'll talk about this a little bit later, but you can look at pulsars in other wavelengths too. So you can go all the way up to gamma and X-rays. And do some pretty interesting pulsar timing applications with those. The one thing I wanted to show you is that because these pulsars aren't bright like the initial ones that were found by Dr. Bell Burnell, you have to fold the data up modulo the pulse period in order to actually see a signal at all, right? So once you know the pulse period of the pulsar, which is something that you can only do after having observed it and detected it, right? Because if you're searching blindly, you're not going to know a priori what the period is. But if you're folding these data, you're getting thousands of pulses, then you're going to bring out this pulse profile that is actually quite stable with time. And so that's a really nice thing, especially about these millisecond pulsars that we observe. They're integrated pulse profiles, even if, you know, from pulse to pulse, the shape is not very stable. There's this sort of jittery effect that happens. If you integrate up all those pulses, what you see is going to be pretty stable. And so that is a very important part of pulsar timing. So I just wanted to sort of show you some more pretty pictures of telescopes, to be honest. But, you know, within these pulsar timing array collaborations, I'm going to talk about them specifically in a little bit. But they're all different types of instruments that are used. Radio telescopes, mostly, except for one thing called the gamma ray pulsar timing array. But it's an enormous collection of telescopes. They all have their own sort of strengths. They all have different collecting area. They all have a different view of the sky. So the actual pulsars that you can observe vary from location to location. And so, for example, if you look at the telescopes on the top that are the ones that NanoGrav, the North American Nanohertz Observatory for Gravitational Waves, our collaboration uses these four. Arecibo collapsed quite a while ago now, which was very upsetting for a whole lot of reasons. It was this really beautiful, as I already mentioned, 300-meter diameter radio telescope. It had wonderful collecting area and great sensitivity for pulsar timing. But if you look at all of these, they're really different, right? So the GVT has this strength of being not only 100 meters in diameter, but also fully steerable. So some people say that it's the largest fully steerable object on land. I've seen that contested, but it's pretty impressive no matter what. Arecibo is extremely large. CHIME, which is the one that's third up there, is very interesting because it just sits there. It's a transit telescope, so it's looking at whatever is overhead. But it means that for the pulsars that it can see, you're looking at them every day. And so that's a really unique strength that the other observatories really don't give you. CHIME also operates at low radio frequencies. And so for NanoGrav, it has, you know, incorporating CHIME data has really opened up the low frequency part of the band to us. And that's complicated, but also a real strength. And then the last one over here is the VLA. So NanoGrav does use the VLA, especially for higher radio frequency observations. But as I already mentioned, you know, there's nothing actually inherently better about having that really high angular resolution, right? Because we're seeing the pulsars no matter what. And so the VLA has fantastic collecting area. That's one, you know, one of the main reasons we use it. But it also has a more southern view, right? So we can see some pulsars that are a little bit too far south for example, the GVT. There are some other really cool instruments that are space-based because these are looking at high-frequency data. So NICER is an X-ray telescope aboard the ISS that unfortunately broke down. There are lots of sort of sad stories on this slide, actually. But NICER broke down recently within the last year. But during its time of operation, it was doing really amazing work. It's called the Neutron Star Interior Composition Explorer. And so they were looking at sort of a set of very bright X-ray millisecond pulsars. And, you know, it's interesting because the X-ray emission is sort of distinct from where the radio emission and the gamma ray emission comes from. It is thermal emission coming from hot spots on the neutron star surface. And that's actually a lot more complicated because you don't have this very simple sort of dipole model. You have to kind of take into account the fact that there might be a different number of hotspots on the surface of the neutron star. They could be different shapes, and that really introduces some complications to your modeling and does introduce a degree of model dependence as well. In terms of gamma rays, the Fermi Large Area Telescope, Fermi's been flying for 18 years or something, which is amazing. It gives us this very long baseline for pulsar timing. We're going to talk about gamma ray timing a little bit later, but the main takeaway I would say is that you're not getting very many photons in the gamma, right? So you really are relying on building up signal over time. Okay, so I think we can move on to pulsar searching. I'm not going to talk about this very much, but I think it is something that's often overlooked in the context of PTAs. It's good to know how we find these pulsars. And so the reason why it's important to think about searching for new pulsars is because of this equation up here. This is obviously simplified. It's a very certain regime of gravitational wave sensitivity. But at its core, gravitational wave sensitivity for the background is proportional linearly to the number of pulsars that you time in your array. So adding more pulsars is the best thing you can do. These pulsars also have to be timed over long time periods, over long time spans, and we have to time them to very high precision. But if we keep adding more pulsars, that's getting us more angular correlations. It's getting us a better sort of view of the Hellingsson Downs curve. And it's just kind of the number one thing that we can do. And that has been true for a long time. So within Nanograv, we actually had kind of a goal of adding something like 60 to 70 millisecond pulsars to the array by 2020. We beat that goal pretty quickly and easily, which was fantastic. One of the reasons we were able to do that is because of these new searches that are targeted searches, and I'll talk about those on the next slide. So if you know where you want to look in the sky, pulsar searching is a lot easier, as you might imagine. There are amazingly effective sort of surveys as well, right? So you're looking at some swath of sky, you're trying to see as much as you can, and you're looking for pulsar signals in those data, but it's very undirected. It's not as efficient as if you have a map, right? As you might imagine. So one of the things that we think about when we think about pulsar searching is the kind of annoyingness of radio frequency interference. So as I already mentioned, we're trying to pull this periodic signal out of a sea of noise, and radio frequency interference abounds. It's pretty amazing. You have noise from different instruments, that are relevant to trying to find the pulsars, right? Your data taking instruments, all of that. But you also have things like outlets, right? Resonating at 60 hertz in the US. You have cell phone signals that contaminate the band. You have all kinds of things that just so happen to masquerade as the periodic signals from pulsars. And so that's a serious complication. And so one thing that happens automatically, or you can do automatically or algorithmically, is searching for RFI based on whether or not it is broadband. So pulsars emit broadband over our relevant sort of radio frequency observing ranges. And so if you see just like a short impulse that's only happening at a small frequency range, then you can be fairly confident that that's not a pulsar, right? We want broadband emission and we want it to be sustained over long time periods too. So if something is just a blip, it's very unlikely to be a pulsar. This is just a sort of a plot showing like how contaminated the band can be. It's not the best visualization, but the axes that you're interested in, the time on the y-axis, this is just the duration of the observation as it goes on. And then the channel number corresponds to the radio frequency that's on the top there. So these are low frequency radio observations. And you can see that the band is very seriously contaminated between about 360 and 380 megahertz. And so a lot of that has to be masked off and you end up losing a lot of sensitivity. So pulsar searching is very hard because you don't know anything about the pulsars that you might find, right? So not only do you have to worry about searching over different pulse periods, you also have to worry about searching over different dispersion measures because you don't know exactly what the DM along the line of sight to that pulsar is going to be. And there's the extra complication, especially for millisecond pulsars, that many of them are in binaries. So, you can see these plots on the bottom are sort of the spread in Fourier frequency. So how smeared out the signal is going to be from the acceleration of a binary pulsar, right? So if you can do trials at different accelerations to account for the possibility of it being in binaries of different orbital periods, then you can kind of condense this, you can get it back into a single bin. But if you are not accounting for that, then it's very possible that the power is going to be spread out enough in Fourier space that you're just going to lose the signal. And so that is very difficult as well. It brings into question this kind of weird balance that you have to make between short observations so that they're not as affected by acceleration over an entire orbit versus the sensitivity, right? Because you would like to observe for longer. but you don't want to be so susceptible to smearing from acceleration. And I guess I didn't mention, so sort of the primary thing that you're doing when you're looking for the periodic signal is performing a Fourier transform. So we don't do this by eye or anything. This is all done algorithmically, but you are conducting, you're doing a fast Fourier transform. You can sort of, if you want to inspect a plot like that, you can pick out the different periodic signals that correspond to RFI, things like that 60 Hertz signal. But you also can sum different possible periodicities over the harmonics that appear in that plot, right? So you want to kind of get out as much power as you can. Some of that is existing at higher harmonics than just the fundamental. And so if you can sum over those various possible harmonics, depending on the period, then you are building up your signal more. So this is just an example of what sort of a, yes, it's a pulsar versus no, it's not a pulsar might look like once they're folded. You fold the data at whatever the sort of like best period and acceleration and dispersion measure is found to be. And so if you've done what you're supposed to, hopefully you'll see a pulsar. Oftentimes you won't. Oftentimes you'll see RFI that was so convincing that it kind of eluded all of your algorithms. But if you do see a pulsar, that's a very exciting discovery. You can see, again, this is the same type of plot that we've already looked at. It's time on the y-axis. It's a single rotation. It's actually two rotations of the pulsar on the x-axis. So you're seeing phase, but it's repeated. You're seeing the signal build up in that reduced chi-squared plot on the right. So that's just showing you that the signal's building over time rather than, some kind of impulsive signal kind of making you build up signal really quickly. And then, plateauing off. So something like RFI might do that. You might not see that just as the observation goes on, you build up signal more and more. You can look at its, the sort of frequency over the radio observing band that's of interest that you're looking at. You want to make sure that that's quite broadband. So you see here that across the entire frequency range, you can see the pulsar. And so that's a very reassuring sign, obviously. So pulsars don't just look one way, right? So these are all millisecond pulsars from various projects, various searches, and pulsar timing array applications, all kinds of things. The origin isn't really that important. I just wanted to give you a sense of sort of how much diversity in the pulsar population there is. And this has to do with a lot of different things, right? You want very high signal to noise, especially when you're talking about high precision pulsar timing. So differences in signal to noise, how bright the pulsar is, the spin period is going to affect this to an extent. Your viewing angle is going to affect the shape of the pulse quite a lot. And so pulsars aren't just one thing. They can have many, many different profile shapes. So really quickly to touch on these targeted searches that I mentioned a few slides ago, this ended up being a really great way to find new pulsars. And so what would happen is that Fermi has these catalogs of unidentified gamma ray sources. And because the gamma ray beam is smaller than the radio beam, you can look for sources that in the gamma look like millisecond pulsars. You can also see that they're not super variable. You can look at other gamma ray properties. But if you just point a radio telescope in a single pointing at that unknown gamma ray source, you often are able to find a pulsar. And so there's a lot of work that goes into kind of creating those source lists. But once you have them, they really are treasure maps. And so that really contributed to, at least a while ago, like of order 10 years ago, a real boom in the number of pulsars that we were able to include in our pulsar timing arrays. There are also highly successful drift scan searches, people who are looking at giant swaths of the sky, looking for all different types of pulsars. In those types of surveys, you'll find a lot of young pulsars. You'll find a lot of kind of radio transients that have these weird signals that aren't suitable for pulsar timing applications, but you will also find millisecond pulsars, and those have been very fruitful too. Okay, so we'll talk about the most relevant thing for today, pulsar timing. So why do we care about pulsars? We care about them because they're clocks and because they're really good tools. And that is maybe underselling how cool they are as astrophysical objects in and of themselves, but that's okay because they're very, very cool. So these pulsars are rotating very stably, right, over time. Millisecond pulsars aren't spinning down very fast. They really are just clocks in space. And so they facilitate some extraordinarily precise timing measurements. So for example, for, that's a typo anyway. For this very well-timed pulsar, we know the period to this precision, right? That's amazing. And that rivals things like atomic clocks. But the reason that's possible is not because we're trying to time every single pulse. We are looking at thousands and thousands of pulses that have been integrated together, and we're looking at the change in that stable profile over time. So if you look on the plot on the right, you can see that between these two vertical lines, that represents about 1,000 times the TOA precision that we're trying to achieve for pulsar timing array experiments. And so that is relative to this being a single pulse phase, so milliseconds. That is amazing. What we're trying to do seems like it should be impossible, but it's not, which is very exciting. So if you want an easy definition of pulsar timing is accounting for literally each and every rotation from a pulsar over long time spans, right? So this method lets us know exactly how many pulses have passed between some time and some other time. We don't, lose phase connection. We don't kind of need to guess at which rotation it might be. We know exactly how many rotations have happened between 2 points in time if we have a solid timing model for the pulsar. So if pulsars were really easy to time, right, you would have something like what's on the top. If it just so happened that the pulses were arriving at the Earth with this, periodicity that really isn't very complicated, it'd be easy to create a model. But the reality is obviously a lot more complicated than that. You have all kinds of delays, in the solar system, at the pulsar, due to the interstellar medium, so many things that do not, cause these pulses to not arrive in that very nice way. Even just the motion of the Earth around the sun is like a very big problem. So we'll split this into two different steps. We're going to talk about how we actually measure the times of arrival, and we're going to talk about how we fit a timing model to the TOAs. Sorry, TOA, time of arrival, as it says on the slide. So this is a little bit weird. It's a little unintuitive, but because you do have to fold so many pulses up to get that stable pulse profile, you are able to compare that against a template that's associated with some good timing model. And it's usually created from lots and lots of observations. That's at least how we do it within our pulsar timing array. So this is like a smooth, sort of idealistic template. And we're just cross-correlating these two things. So you have your folded observation, you have your smooth template, and the phase difference at which this is maximized, right? This correlation is maximized, gives you some delta, delta phase. And so what that tells you is that you have some sort of mistake, kind of. It's not really a mistake, but it does mean that the model is not predicting exactly the time at which the pulse should arrive. And obviously this is not actually one pulse, right? We're not fitting this to like single pulses of a pulsar. We're doing this for the integrated data. And so once you measure that phase shift and you multiply it by the period of the pulsar at that time exactly, then you get a time difference. You add that to some known point in your template, and that is basically what a TOA is. So this is sort of the origin of measuring that difference. It's kind of telling you how well you're doing, and the process really is iterative. So as we improve our timing models, our ability to predict what that phase shift should be improves significantly, and that is very powerful. So how well we can measure the TOA is a very complicated question. I really just want to point out some of the important factors to remember. So you don't have to worry about every single term in the equations on the left. I just want to point out a few things. So obviously, as you might intuitively think, the signal to noise of the profile is very, very important. We really want the pulsar pulse to be rising well above our noise floor. We also want pulses that are kind of as small as possible, right? And we want pulsars that are spinning really rapidly as well, because that's just getting us more data points. So if you have, more data points to sample, then you're going to be able to do your timing more precisely, which is a very powerful thing about millisecond pulsar timing specifically. But yeah, so you can see from these, like if you wanted to pick out the best pulsar for pulsar timing array, and all you could go off was the profile, what would you choose? Yes, beautiful, exactly. That duty cycle is really small, which really improves your timing precision. Its signal to noise is very high. We also think about things at the telescope, like if you're observing over a larger bandwidth, that also improves your timing precision quite a lot. If you have a longer observation, as you might imagine, that's also improving your timing precision. And so those are sort of some of the things we try to balance. Large telescopes are better than smaller telescopes for getting highly precise times of arrival as well. And for pulsar timing array applications, we're often going for at least 1 microsecond RMS timing precision. So it's a fairly difficult thing to achieve. So it's not as easy, though, as even just measuring the time of arrival, right? So you have to transform the time of arrival into something that is roughly inertial. And so you have to use a model of the solar system and sort of where the center of mass, the solar system barycenter is, in order to correct your time of arrival. Because it wouldn't work if you were just tagging the time when it arrived on Earth. There are other things to consider with the solar system barycenter, like the models that we're reliant on do change with time. They improve over time. I think we heard about this a little bit yesterday. But we do rely on having a good model in order to do the transformation of the time of arrival of the TOA. There are delays, obviously, if the pulsar is in a binary, you have to account for that difference in sort of light travel time. You have to worry about the sun and the delays the sun causes. You have to worry about your observatory clock, so you have to have an extraordinarily precise clock that lets you sort of transform to something like GPS time, which can then be transformed into some other time standard. We're not going to get into the details of that because it's not that exciting. But there are all these transformations that have to happen before you can actually do this pulsar timing thing well. So the sort of key here is that pulsar timing is powerful because, between any 2 times of arrival, we know that there's an integer number of spins, right? That's highly constraining. And so if you look at this Taylor expansion on the bottom, which is sort of, it's accurate once you've done all the transformations we already talked about, you are looking for values of, for example, the frequency or the period of the pulsar and the frequency derivative. You're looking for values that cause any 2 TOAs to have an integer number of turns between them. And so that is the reason why pulsar timing can achieve sort of such high precision. It's not that we're able to kind of observe every pulse. It's that we, are able to integrate up these stable profiles, and we know that turns are going to be integers, right, as you might imagine. The only thing I wanted to show with the plot over here on the right is just that, if you have, this is the smooth template on the top, the data on the left are from 1600 megahertz, data on the right are from 750. You have to have different templates depending on your observing frequency. Yes?
Why the first implement is equal to get adding more terms? Like that's only making an answer, like just adding.
Oh, but it's just the so that's kind of getting you the time shift difference. And then everything else is being transformed. So it's not like that's not like the T not there is not the same as the other parameters in the equation, right? So you're trying to find the time difference. And then onto that, you are adding all of these different corrections for, you know, binary delays, solar system delays, things like that. Does that make sense? We can talk about it more too if you want. Okay. All right. So the kind of currency of pulsar timing is timing residuals. Well, the currency is TOAs, but the thing we think about a lot when we're talking about pulsar timing arrays is timing residuals. So the difference between the predicted time of arrival and the actual measured time of arrival is a timing residual. So you can see that if your model is doing a good job, you get these sort of nicely distributed TOAs on top. There's not much structure. You're not seeing any sort of errors in your timing model. But even a 1% error in, for example, the spin down rate of the pulsar induces this quadratic, you know, mess up over time, right? You don't want to see that structure. That means that there's something fundamentally wrong with the model that you're using. Different things manifest in different ways. So position errors obviously will change on the kind of 1/year rate. Proper motion grows over time because that's, you know, not something that's periodic. The kind of difference in your prediction and your measurement is going to be worse as time goes on. You can also detect, for example, exoplanets around the pulsars. This is how the first exoplanet was detected. You just see this nice periodic signal manifesting in your data. It is never that obvious. This is like a very severe cartoon. Yeah. So I wanted to sort of give you an example that I stole from my colleague Tim Panucci about what phase connection actually means. So you can have a timing model that does pretty well over a short amount of time. But then if you look away and then you look back, maybe the model's not doing well enough to actually tell you exactly how many rotations have happened. So it's a little bit like if you're dancing and you're on beat, you're really feeling it, right? As long as the music's playing, right? As long as you're observing, you can sort of stay on beat and it's not too bad. If the music turns off though, and especially if the music turns off for like months, but you know, realistically in this example, we're talking about minutes or maybe seconds, it's going to be really hard for you to stay on beat after a lot of time has elapsed, right? And so knowing that you are actually, you know, not just on beat, but you're also on the correct beat and that you have let enough time elapse is very hard, as you might imagine, on the dance floor. Okay, I want to check the time we have. 10:30. Okay, we should start zipping through this probably. So pulsar timing, you know, in its most basic state, we usually use just chi-square minimization to fit our timing models. You can do much more complicated, more astrophysically informed things. If you're looking, for example, at Markov chain Monte Carlo modeling, that can be a really great way to sort of impose knowns on the parameters, right? You can say, you know, a lot of things, you know, for example, parallax isn't negative, right? So that's an example of a really good prior you could put on one of your parameters. But it's more computationally expensive. There are a lot of different ways of actually extracting these TOAs, and we didn't talk a lot about what you're doing in frequency space. So your band can be chopped up into multiple, you know, kind of chunks of frequency, right? And so the traditional way, the kind of narrow band timing way, is to get one measurement of a time of arrival per frequency chunk. That gets you, in this example, 11 time of arrival measurements. But if you could instead have a model for what the pulse does, what the pulse profile does as a function of frequency, then you could extract information in one go, right? So you can measure this dispersion measure sweep, you can measure changes in the profile over frequency, and you can get out a single time of arrival measurement. That's really, really good for computational reasons. So in the nanograv data set, it reduced, you know, the difference between the narrowband and wideband data set for the 15-year, it was smaller by 33 times. So that's really important when you're doing gravitational wave analyses. Things have gotten better with better computing, but it's a very good thing to reduce the size of your data set. So in pulsar timing, we're thinking about noise on different scales. So there's intrinsic noise to pulsars. There's jitter noise from pulse to pulse. There's radiometer noise, so just white noise that is associated with instruments that you're using to take your measurements. And then you have this like intrinsic noise from the kind of rotation of the pulsar changing very slightly over long time periods. That's achromatic red noise. And then you can also have chromatic red noise from mistakes in modeling your dispersion measure variation as a function of time. And so you can see on the rightmost plots, top one is achromatic red noise. This is just a pulsar that shows very strong intrinsic red noise. You can also see that its DM variations are very strong as well. So the middle plot is showing you change in DM versus time. And then also, if it comes close enough to the sun, then you can see this annual contribution from the solar wind as well. And so that has to modify your measurement of the dispersion measure. And it's really important for those pulsars that have, small elongations. Matt's going to talk about this a lot more, I think, in the tutorials and some sessions next week. So stay tuned for that. I don't think we need to go through this. The one thing I want to point out is that when we've been talking about all these possible kind of mistakes that can happen in pulsar timing, things like clock errors, things like problems with your solar system barycenter measurement, those are inducing correlations that are almost certainly not quadrupolar, right? So problems with the solar system ephemeris is going to give you this dipolar signal. Problems with your clock are going to look like a monopole, but nothing that we really know of is mimicking the gravitational wave quadrupole in a way that is too concerning for us. So this is a very good thing. Pulsar timing is very cool though, because you can use it for other things besides pulsar timing arrays as well. Because the dispersion measure is such an important factor, you can study the interstellar medium and, kind of learn about its structure, learn about what's actually happening to the signal as it passes through on its way to you. You can also use pulsar timing for very precise tests of general relativity. You can measure neutron star masses very precisely, which I'd like to talk about in a second. Pulsar timing arrays have the ability to probe physics beyond the standard model, which you'll also hear about next week. So pulsar timing has really resulted in some pretty amazing findings. Having these space clocks is extremely convenient. So the next thing I want to talk about is just a very specific sort of thing we can do in a subset of our binary pulsars. So if you have a timing model for a binary pulsar, the normal model is going to get you these 5 Keplerian parameters that describe the orbit, right? Things like the orbital period, the eccentricity, the size of the orbit, stuff like that. But if the system shows kind of GR effects, then you have to account for those with extra parameters, and we call those post-Keplerian timing parameters. And so the reason why this is so strong, or why it's so important, is because, if you plug these kind of Keplerian parameters into the mass function, you can't kind of tell the difference. You have a degeneracy between your parameters, right? So if you're interested in, for example, measuring the mass, you need more information in order to break the degeneracy, for example, between the mass of the pulsar and the mass of the companion. And so being able to measure those post-Keplerian parameters very well is one way to go about doing that. So normal timing is not necessarily going to get you a measurement of the pulsar mass, for example. So I'm going to focus a lot on Shapiro delay parameters. They're described with R and S, which sort of show you the shape of the Shapiro delay. We'll see a plot of that in a second. But really quickly, I wanted to mention, I think Alexander already talked about Hulse-Taylor binary. So we don't necessarily need to go over that again, but it was a really strong test of GR. There's also 0737, which is the double pulsar. This was a pretty amazing system. It's very compact, very eccentric. It let them measure, all of the post-Keplerian parameters, right? So with enough time, they were able to get kind of measurements that support each other, right? They don't just have the 2 parameters that are necessary to break the degeneracy. They have more than that. So they can test the consistency of their parameter measurements. And that was a pretty amazing thing to be able to do. We don't know of that many neutron star binaries. And so it's not something that's done often. The reason why I want to talk about measuring pulsar masses is just because we don't understand the structure of neutron stars very well. So we sort of have an idea from experiments that are able to be conducted on Earth about the neutron star crust, about what's happening just under it, this kind of fermionic, this like super fluid. But as you get denser and denser and denser, the physics becomes really confusing. So when you're at the point of being a few times nuclear saturation, it's really not possible to test that in a lab on Earth, right? And so the really great thing about this is that observable parameters can be pulled from these different equations of states. The equations of state are describing the change in pressure as a function of density. That's one way of like kind of visualizing it. But this is great because it transforms directly into a mass versus radius. So if you're able to measure the mass of the pulsar quite well, you are able to put very stringent limits on these different kind of propositions for the equation of state. So for example, if we find a 2 solar mass neutron star, but there are some equations of state that don't allow for that to exist, they say the neutron star would have already collapsed, then you know that the model has to be sort of reconsidered. And so it's a very straightforward way of kind of constraining that parameter space. So the Shapiro delay is one of these kind of post-Keplerian effects that happens when the pulsar goes behind its companion along our line of sight. The pulses are delayed, as they pass through the line of sight towards the companion. And so you see in the timing residuals this very distinctive delay. And it looks like this. So we're taking the kind of point at which the pulsar is behind its companion as happening at orbital phase of 0.25. You can see where the Shapiro delay signal peaks there. And if we're able to measure that quite well, then those R and S parameters are what we're able to combine into the mass function to get out those distinct measurements of the pulsar and its mass. The pulsar's mass and the companion's mass. This is a little bit weird. So you can see there's like a dim signal behind the bright one. The bright one is the one that we can actually measure. So you can see that this is a timing delay. This is for a very specific system with 2 specific masses and, inclination and everything. But it's not very big. It's like of order 10 microseconds, right? And so it's really in a very small subset of systems that we're able to do this. The other important thing to look at is just the strong impact that inclination angle has. So we can only do this for systems that are effectively edge-on. But if we do have an edge-on system and it can be timed very precisely, then that's a very powerful tool. So I don't know. I don't think we need to go through all of these examples. I do want to mention quickly at least the first kind of really groundbreaking measurement of pulsar masses using Shapiro delay. This was from Demarest et al. In 2010, and they were able to measure the mass of J1614 to be around 2 solar masses. And so this immediately put pretty tight constraints on the interior neutron star interior equation of state. It ruled out a lot of sort of exotic theories for what might be happening deep in the core. And you can see the plot on the right from that paper looks exactly like what we were seeing before. You have the actual full signal, and then you have the measurable signal. So the full signal is what would happen if you didn't have to fit for any other timing parameters. The measurable signal is what you actually have access to because you have to fit for other timing parameters in your model. There have been other, obviously, notable measurements of Shapiro delay. This is happening more and more, especially as there are bigger instruments that are able to access more pulsars. That's been really fantastic. There are some other famous examples. There's this sort of disputed 2.34 solar mass neutron star that hasn't been measured super precisely. This is not done with Shapiro delay. It's done completely differently with white dwarf spectroscopy. But it's certainly intriguing. It's exciting as a possible kind of really far out there blip in the population in the distribution of masses. Okay, let's not go through all of these. These are some sort of specific examples of kind of various measurements that you can make with different types of observatories. We can go back to this if anyone wants to. I wanted to mention really quickly multi-wavelength timing. So this is what I was describing with the X-ray data. So these are coming, the pulses are coming from hotspots rather than from the sort of beamed emission like in the radio. But the hotspots have to be modeled. And so this is thermal emission. This is not non-thermal emission like what we get with the radio and the gamma ray data. And so the complications are very different. It has different strengths. But X-ray timing is very cool. It's been explored as a possibility for navigation. So X-ray navigation is possible as a way to kind of steer spaceships and not be reliant on GPS and do things like that. So I just wanted to show you really quickly kind of the difference between the radio data and the gamma ray data. So in the gamma rays, you're actually detecting individual photons, right? That are kind of collected and time tagged by Fermi. And so you can't, you don't have this continuous radio signal. You can't kind of integrate over all of these different rotations in the same way that you can with the radio data. And so you have to do this single photon timing technique. And so you start with some assumed profile. For each photon, you're predicting the phase. You're trying to figure out how likely it is that that photon actually came from the pulsar. And you're optimizing this. And in the end, hopefully, you get something like this. This is 1231 minus 1411. It's like the best gamma ray pulsar. And from this pulsar, we get 1 to 2 photons a day. So that really demonstrates why it's not possible to kind of use normal pulsar timing techniques on this kind of data. But it is very powerful in its own right, because the gamma ray data isn't sensitive to things like dispersion measure variations, right? And so we have this sort of desire to do joint timing techniques where you're using both the radio data and the gamma ray data in order to kind of parse out what might be red noise from intrinsic red noise variations, right? From kind of spin noise, and what might be from mismodeled dispersion measure, so chromatic variations. And so if you're able to look at those two data sets together, you can do a much better job of parsing out kind of what noise process goes with what. And we're doing some pretty exciting stuff. So there's this thing called the gamma ray pulsar timing array. It's exactly what it sounds like. We're using the Fermi Large Area Telescope and the very long data set that we have in order to try to make the same sorts of constraints on the gravitational wave background as we can with radio data. There are a lot of, kind of deficiencies in gamma ray timing. The lack of photons is a really notable one. But it was really surprising to everyone. This was demonstrated in 2022 in a paper led by Matthew Kerr, that we are actually approaching the point where we can make constraints, at least upper limits with this limited data set, on the amplitude of the gravitational wave background. And we're hoping that with time, as this data set builds up, that we can actually make a measurement. And we think that we're approaching a sensitivity that will let us do that. And so that's very exciting stuff. We're going to publish that data set this year, so look for it. Questions, break. I'm sure plenty of you are annoyed with me, so I'm happy to take a break or just keep going for a minute. Yes. Holy cow. Okay. Front table first. Yeah. Okay. No, that's good. I'm excited that people have questions. That's a very good thing.
I think what I'm curious about is in hotspots that you detect this Fermi, do they ever shift around pulsar? Or are there any variability in how they appear or disappear, anything like that?
So that is not with Fermi. Oh yeah, sorry. So the question is, do the hotspots move around on the surface of the neutron star? And that is with the X-ray timing, not with the gamma ray timing, but because we're talking about the thermal emission. Over long time scales, I think that's certainly possible. Over the durations that we're talking about when we're looking at our timing observations, that is not the biggest source of uncertainty. We're a lot more worried about kind of the shape of the hotspot, even just the number of hotspots. But it is, I think something that has to be kept in mind for long duration timing experiments. Yes.
Yeah, I'm just wondering what percentage of total pulsars in the galaxy do you think we found?
Oh, that's a good question. So a lot of pulsars are going to be quite faint. In terms of a percentage, I don't have that off the top of my head. I'd have to think about that a little bit. It is completely a function of like our available instrumentation, right? Because pulsars are quite faint. We really need good, large radio telescopes to detect them. And so the pulsars that we know of are quite nearby. So it is a small portion of the population that we're actually able to access. I can think about the actual percentage though. That's a good question. Yeah, yes.
So I was a little confused as to how you know that you have a pulsar. Like if you just were given raw data, how do you know that you actually have a pulsar? Because I understand that you have a bunch of waveforms or you have a bunch of templates, but that template is to kind of refine the pulsar itself, if I understand it correctly.
So yeah, there's sort of two issues here, I think. And I think your question has more to do with searching for pulsars, right, than with timing them. So searching for the pulsars, you don't have to know exactly what the pulse profile looks like. You just have to look for a periodic signal. And so, you know, the complication in the searching is that you have to search over a bunch of different dispersion measures because you have to properly realign your data, or else when you integrate over the data, they're not going to be, you're not going to come out with a signal. You have to worry about acceleration like what we talked about, but you don't actually have to have like a template for the profile itself. You just need to be kind of getting the parameters good enough that when you go through and you refold the raw data, you can see whether or not a profile comes out. So like a lot of the time with an initial detection of a pulsar, the profile will look kind of not so good because, you know, either you have the position slightly wrong, you know, that's kind of the biggest culprit. But yeah, you don't have to know it exactly. You just have to know it enough that you're not like losing coherence over a single rotation of the pulsar.
So then how do you correct this version? Because it seems like from looking at different frequencies,
yeah,
it's not entirely clear to me that this specific part of that frequency, that this specific frequency is the same as the other way.
I'm not sure if I totally understand the second part. I can try to address it though. So, I mean, with the searches, like one of the reasons why they're so computationally kind of demanding is because you are like just testing trial DMs. So you're just saying like, let's imagine the DM could be anything between 5 and 300 or whatever. And you're just going to do a bunch of trials and you hope that one of those is close enough to the actual DM that you can see the pulse come out of it. So it's kind of, it's not that elegant. It's not as elegant as what I think you were describing. Yeah.
Related question. The first is, how many gamma ray pulsars are you timing in order to get some traits on, you know, everything like that?
Yeah, so for the data set that came out in 2022, DR1 as we're calling it, I think it was 36 or something. But in this second data release that we're working on right now, we have 80 gamma ray pulsars. And so it's not quite the same as radio where we expect to find a lot of new ones. But there certainly are ones that are now viable because we've been timing them for longer. But yeah, 80 pulsars, so it's not so bad, kind of cool.
And then the second question, especially with nicer breaking, is there potential for, if nicer is in lower orbit, you can potentially just put like a bunch of CubeSats, you know, in lower orbit and detect like a ton of pulsars at the same time?
So I think I'm not really an expert on CubeSats, but I think one of the real complications with NICER is that you have to know your position quite well, right, in order to make these corrections. And I would be surprised if you had if it was easy enough to make a CubeSat that could support a detector that's large enough, and B, you kind of have the stability that's necessary that you can get through a spacecraft, you can get through the ISS, in order to have kind of a level, stable playing field, I guess, if that makes sense.
This is a very question. Can you show the action? Can you show the sequence from observation? What causes spread in the
Oh, in the profile itself? Yeah, so. Yeah, right. Why isn't it just like a single impulse? I mean-
it's not the result. And then, but it's the gravity, time delays and whatever, we get that position of peak would cause spread.
Yeah, so that's a fantastic question. If we're just talking about like all other things being equal, if we look at a pulsar, at a high radio frequency versus a low radio frequency, they're a lot more susceptible to scattering at low frequency. So a lot of these kind of problems that we talked about don't affect the actual shape of the profile. They affect, as you already said, kind of the time of arrival of the pulse. Scattering is sort of unique in that way, that it really does broaden the pulse itself. But it's also important to keep in mind that you're looking at the beam as it's sweeping across your line of sight. So it's not like you're actually looking at like a very, very quick impulse. You are seeing it as it crosses, and it has, it's this geometric thing. The kind of emission isn't necessarily going to be exactly the same over the entire beam. And so you get this different viewing angle. And that is why it's not just kind of like a real clock pulse or something. That makes sense. Yes.
I,
Oh, did I mess up? Sorry, with calling on people. That was not intentional at all. I'm really sorry.
I have heard of pulsars glitching.
Yes.
How do you account for that timing problems if you do?
Yeah, great question. So these glitches happen because of kind of interactions between the kind of fluid outer core and the crust of the neutron star. And so this doesn't really happen very much in millisecond pulsars. It's much more of a problem for young pulsars. So for pulsar timing arrays, there's like one example of a glitch happening. And it ends up being a step change in the period of the pulsar. So it introduces a lot of complication. It's really not something that we want to have to deal with in the pulsar timing array applications. But it really is like an instantaneous change in the period. So it's modelable in that way.
How we can say, just looking at the graphs, that it's a binary, it's not just two pulses at different locations, just on the same line of sight. It's not that. Or it's like, how do we?
So, right. So when you do an observation of a pulsar, obviously this is not quite true for ones that have really long orbital periods. But for ones that have sort of normalish orbital periods, you see the apparent period of the pulsar changing over the course of the observation. And that's actually that's kind of like a problem because you have to know exactly what the binary orbit is in order to correct for that, right? And so what you end up getting is actually like this apparent change in the period of the pulsar that's sinusoidal over multiple different observations. And so that's how you start kind of parsing out what the binary orbital period might be, because you see it directly as you're observing. It's like a very obvious change in the period. And so I wouldn't imagine that, the setup that you're talking about would necessarily induce that very specific sort of sinusoidal variation. There are other things to think about too, like just the coincidence. It's like very unlikely, I think, that you would get into this situation, right? Yeah, so.
The dispersion measurement, like when we make our distance priors for detection, for dispersion measurement, we choose different steps for different ratio of dispersion measurement. Like some of them are Gaussian, up to 0.8 LDN, then some of them are Gaussian, and some of them half Gaussian. Why we choose that kind of thing? Like, I don't know.
I'm sorry, I don't think I quite understand the question. Can you repeat it?
When we make our distance priors, there's one part is parallel and another part from the dispersion measurement.
Right, yes.
Dispersion measurement, you choose different steps according to the dispersion length. Like some of them are half Gaussian, some of them are Gaussian. Why we choose different steps here for the distance priors?
Let's see.
Do we choose one of them?
Yeah, for 0.8, like the API model. It's just the middle part is crossing and the other parts are not crossing. Like according to the current finding.
I mean, my first guess is just that if we're going off of electron density mapping, it's very unlikely that you would have as, you know, as much of a probability of the DM being way lower as you would for it having a pretty significant tail. So I think that sort of makes sense. And then the error on the parallax is going to be Gaussian just because that's how our measurement works. Yeah. That's my guess, but I'm actually not sure. I would need to look it up. Yes.
How do you model those covariant parameters? You were talking about.
Yes. So in order to actually be sensitive to the post-Keplerian parameters, which, you know, the changes in the pulse arrival time that they induce depends on the parameter that you're actually talking about. So things like orbital decay, you need to look over a really long time span. So you don't start to even see it in your timing residuals until you've observed the pulsar for quite a long time. Things like Shapiro delay, you know, again, you have to have this very specific geometry, and the signal manifests over a single orbit rather than over, you know, sort of decaying over time. And so these are like small corrections to your normal measurements, but they become more and more important as time goes on for things like orbital decay. Does that sort of address what you're talking about? Okay, great.
You're back over.
Okay, so let's take a 15-minute break and then we'll come back with a work derivation from me and when we get, we'll start to respond to gravitational waves, okay? And then at some point, punch will back.
Are we? Stop, sure.
Okay, slight change of plans. Thankful has more to say. So here's some more.
So-
And then that'll take us through to lunch.
You guys aren't gonna be clapping by the end of the segment. So the other thing I have prepared is much more nitty-gritty and much less interesting theoretically. So I hope it will be of interest to some folks here, but if you fall asleep, I will not blame you at all. Okay. If we're ready to get started, let's do it. So I want to talk to you a little bit about what like a PTA data set actually is, right? Because we're here for kind of gravitational wave purposes. The most relevant thing that you might be getting out of this, if you're not interested in the pulsar timing itself, is like, what data products are you actually going to have access to? What do all of these things mean? And so I wanted to give just a really quick overview because I don't think we've introduced this formally. I'm going to be talking about data sets from various collaborations, but the International Pulsar Timing Array, the IPTA, is like this global consortium. We call it a consortium of consortia because each individual PTA is its own consortium as well. But the goal of this is that there are all these PTAs all over the world. They have their own instruments. They have their own sort of expertise. These instruments differ greatly in sort of what their strengths and weaknesses are. But we know that if we try to pool all of our data together, we will have more sensitivity to gravitational waves, right? That is the thing that we would do ideally. And it is something that we've done on several different occasions, but it's extraordinarily difficult. Because the instruments are so different, because we all have different philosophies about, for example, how times of arrival should be extracted, how noise modeling should be approached, things like that. It's very easy to have disagreements in how the timing is done. But if we can pull all these data sets together, we gain a lot of sensitivity, and there are lots of new techniques, or not lots, but there are some notable new techniques emerging that don't actually require you to pool all of the data into a single data set. It lets you analyze kind of what each PTA is saying, this is the best solution I have for this pulsar. Now do a gravitational wave analysis with that. And so that takes a lot of the complication out of it. So NanoGrav, as I already said, North American Nanohertz Observatory for Gravitational Waves. We talked about this a little bit yesterday. We're a physics frontier center. This is a picture from the Vanderbilt meeting in 2021, which I thought was really cute. We use these beautiful telescopes we already talked about. We have about 20 years of data now. It's actually a little bit more. And we have tons of people who are involved in the collaboration. So I'm not sure if everyone here is sort of at least tangentially involved in NanoGrav, but I do hope to see everyone at collaboration meetings and such. So I wanted to give an example of what a pulsar timing program actually looks like. So this is only NanoGrav. This is not any of the other PTAs. But there are several different things that we're trying to optimize here. One is that because of dispersion measure variations, we want to be observing at two different frequencies if we can. So every pulsar should not have just like one observing band that's being used. We want to be able to compare, relatively high frequency and low frequency data. This is totally like a function of what instrumentation you have access to. I already mentioned CHIME works from 400 to 800 megahertz, so that's relatively low frequency. But CHIME really helped us after we lost Arecibo, because it meant that, for the pulsars that we had to move from Arecibo to the Green Bank telescope, we were able to, for the majority of them, already have low frequency timing. And so we didn't have to do, 2 bands worth of timing at the GBT. And so what you'll see in a lot of different collaborations data sets is that they have this dual frequency observing scheme. I can mention it a little bit later. There are other approaches to this. So at the Green Bank telescope, we're getting an ultra wideband receiver. Parkes has this as well. But that's going to let us look at a very wide range of observing frequencies from like 750 megahertz to 4 gigahertz. So that's very, very good for dispersion measure variations. There are some other questions about kind of optimizing for positions of pulsars on the sky, right? You want all of these different pairs of pulsars to create as many different angular separations as possible. We've done some searching for pulsars that actually is it's targeting like, it's a little bit, I mean, it's basically informed by the Fermi targeted searches, but it's really honing in on the pulsars that are in parts or the potential pulsars that are in parts of the sky where we're lacking gravitational wave sensitivity. So you can think about optimizing in that way as well. Yeah, so this is where it gets really not fun. Oh wow, it's actually also really hard to see. We can look at the website instead. So I wanted to just show you what some of these data products look like. So here's a repository of all of the pulsar timing solutions that we currently have within Nanograv. This is for 80 millisecond pulsars. It's a lot of pulsars. And you can see that we sometimes break up our data by observatory, things like that, but the like main data set is going to use observations from every observatory all at once. And so, for example, this is a PAR file. So PAR is short parameter. It shows you the components of the timing model. And so this is getting to be less and less true because there's a lot of infrastructure now built up around kind of making the timing process easier. But this in the olden days, I guess, would be where you designate whether or not parameters are being fit as well. You can see for this pulsar, which has been timed for, all of Nanograv, a very long time, we have all of these jump parameters. And that's because we need, for every combination of telescope backend, so like data taking instrument, and front end, so receiver, we don't necessarily expect to be able to kind of coherently measure the differences between any one set of those two things. So every time there's a change in the front end or back end, we need to put in a jump, which is just a DC offset in the timing residuals. So that goes into the model there. You can see why. So we're moving away from DMX. DMX is this like piecewise constant way of modeling dispersion measure, where we have these different bins corresponding to different epochs of observation, and we're measuring the difference in DM in every single one of those bins. We are trying to move past that. This has been done very successfully with Gaussian process, DM modeling, and more sort of advanced techniques. But right now, the data set does have DMX parameters, so this is like not a joke. These are all fit parameters. Actually, let's look at the good ones first. I got too distracted by the DMX. So you can see some very obvious things. You can see, for example, the solar system ephemeris that's being applied. You can see some, information about the data set that's not necessarily describing any parameters, like the length of the data set. But then you have fundamental parameters. So you have things like F0, F1. Those are like the two things you need to have if you have a timing model. You have the position on the sky. You can do that in different coordinate frames if you want. You have other astrometric parameters. So you have proper motion in both directions, and you also have parallax. That's where all of these things are defined. So these are sort of fundamental parameters up here. Then you have the jumps that are showing the differences in this kind of truncated or chunked up data set. And then you have parameters describing the DM from epoch to epoch. Cool. And then we get down to some more interesting parameters. So one thing we see is, well, we don't need to talk about FD parameters, but I wanted to just show you that when noise modeling is conducted, you get best fit values from that noise modeling and you put those into the pulsar timing model. So those aren't necessarily in this scheme, how we have it set up here. Those aren't necessarily being fit. They can be fit simultaneously with the timing model, which actually has a lot of benefits, but they're not. And then, for a binary, you'll also have all of the binary parameters in this part of the PAR file. You'll be able to see the binary orbital period, eccentricity, the semi-major axis, all those things. And post-Keplerian parameters are included in that as well. So there's important information after all those DMX bins. So that is a PAR file. And this is a TIM file. So it's quite messy as well. The sort of fundamental things that you can see here, TIM is for TOAs. These are just your TOAs, right? They're time files. And so what you see is like which template, which profile, rather, the actual TOA measurement is coming from. And then you see things like how good the measurement is. So here is the name of the file. And then you have the frequency at which it was measured. You see here that even for simultaneous observations that are like very close together in time, this is MJD, you can see that because we're splitting the band, the frequency band, into a bunch of different pieces to get multiple TOAs, you can see that the frequency is different. It goes across the entire band for multiple TOAs that appear at basically the same time. You have the uncertainty on your time of arrival measurement, you have the telescope it was taken at, and then you have all these flags that we don't need to go through. They tell you things like which combination of back-end receiver the TOA actually comes from. There's like a goodness of fit measurement for the TOA extraction. You know, it marks which channel, so which part of the band the TOA is actually coming from. It gives the measured signal-to-noise ratio. And so having all of these things sort of defined separately is really important because the data set is so large at this point that we want to be able to make cuts based on like specific properties of these TOAs, right? So you could very easily, with modern software, say, I don't want to see any TOAs that have, you know, that have like uncertainties associated with them that's worse than XYZ. And so that's really helpful. You can also, you know, cut by signal-to-noise ratio, for example. In Nanograv, we don't use TOAs that are coming from profiles with signal-to-noise less than 8. That's just like picked as a kind of a good demarcation. If you're doing IPTA work, so if you're combining data sets, you also want to know which pulsar timing array the data are actually coming from, because these will eventually all get combined together. We try to be very careful about sort of versioning and everything like that. So I wanted to just show you the kind of basic data formats, the data products that are available as part of pulsar timing array data sets. So PAR and TIM files are the really important thing. That's the real currency. Okay, so we don't need to look at these. I did want to just shout out the fact that you can go find the data if you want to play with it. The pulsar timing software that we use to do a lot of our work, all of it's publicly available. There's several different sort of generations of pulsar timing software. The most recent and probably easiest to learn one is called Pint. Matt Miles is going to do an introduction to that with you on Thursday. But you can go grab that software if you just, it's in the Nanograv GitHub repo. You look up Pint and you can find sort of some tutorials to get started. Yes?
The companies in the far there are places where each of them clearly defined kind of parameter.
Ah, yes. So I think that if you go to Pint and you go to the documentation, every parameter should be defined. There's also a really iconic paper associated with a different timing package called Tempo 2. And I know that the parameter names are published there along with like the units that are being used and everything. So if you aren't able to find that, I'm happy to point you to it. Yeah, just let me know. Yes. The feather files? Yeah, so I do think that I think that the feather files can include both of these data products, but they don't necessarily by definition. I am not sure what our like ultimate data product is going to look like, but it is pretty convenient to be able to pull out the associated PAR and TIM files. And the TIM files are really big, so that is like one problem with that. But at least knowing what the timing model parameters are can be really helpful when you're looking at those files. Yeah. Okay, cool. So I don't really want to get into a lot of detail about this, but I did want to sort of advertise that within Nanograv, we're working on the 20-year data set right now. And so you can see the growth of the Nanograv data set with time. On the y-axis are different pulsars. On the x-axis is time, obviously. And so you can see that for the 5-year data set, it was quite a small collection of pulsars. We had 17 pulsars timed over 5 years, 5-ish years. The 9-year data set, we added some more pulsars. Obviously, that's really important for gravitational sensitivity. Same with the 11-year. There are sort of not even gaps in the amount of time that it took us to make these data sets or that we chose to make these data sets in. The 15-year, which was the one that was sort of released alongside all of the other PTAs and kind of resulted in evidence for a gravitational wave background. That one was really exciting because we added a lot of pulsars between the 12.5-year and the 15-year data sets. And that was like a very powerful thing for us. In the 20-year data set, we are adding a handful of pulsars. We've slowed down on our rate of adding sources after we lost Arecibo because our overall observing time available is much smaller. And so we had to be very careful and strategic about which pulsars were being kept in. We do very occasionally like kick pulsars out as well, but that's kind of fewer than 5 that we've kicked out. Actually, that's not true because when we transitioned from Arecibo to observing those pulsars at the GBT, we lost 6 pulsars that were observed at Arecibo. And then there have been a couple that are only in the GBT part of the data set that we've also kicked out just because our ability to time them is worse than we thought it was going to be. There's some other exciting changes. So, I showed you the like burning computer trying to tackle all of these TOAs. These are for narrowband TOAs, so we're not using any kind of advanced wideband timing techniques. And the 20-year data set has like more than 1 million TOAs. So it's beefy for sure. It's pretty scary, to be totally honest. There were 675,000 in the last data set. So pretty serious. One of the reasons for that is because we added, for this 20-year data set, it's the first time we're including data from the CHIME telescope. And that's the one that works at low frequencies that looks at pulsars that are available to it every single day. And so if you have, rather than the normal monthly measurements that we get, if you get those daily measurements, you obviously are creating a lot more data, as you might imagine. We also, in our last data release, switched from using Tempo to Pint. So Pint is that software package that I mentioned. Strongly recommend if you're interested in pulsar timing, looking it up. Matt will talk to you about it as well. Yeah, we don't need to talk. There's also like a new backend, a new data taking system at the GBT that we're switching to. That introduces its own complications. Yeah. Any questions about this? The colors, if you're wondering, correspond. I don't have the key on here, but they correspond to different combinations of backends and receivers. So it's sort of like different parts of the data set. And you can see that some pulsars are, only visible with one observatory, or, we obviously look at them with multiple observatories or whatever. Okay, and then IPTA data sets, as you would also imagine, are even bigger. So this is where you're trying to combine individual PTA's data into a single data set. For the most recent published one, DR2, there were 65 millisecond pulsars in total. But DR3 is going to have in the 130 range, which is pretty amazing. So it's the first time we're including data from like the Chinese pulsar timing array, which uses that really amazing FAST instrument that's larger than Arecibo. It's the first time we're incorporating data from LOFAR, which is a series of dipole arrays that are actually sensitive to very, very low radio frequencies, like below 100 megahertz. And so there are all these changes that are being made that are complicating the process of trying to combine these data sets. We're also, I mentioned that we have different philosophies about how we like to do our pulsar timing. There are some groups that are using Tempo 2. There are some groups that are using Pint. And so we wanted to demonstrate for these pulsars that the solutions we were getting with one package versus another are consistent. And so there are some people working on like a Pint pipeline and some people working on a Tempo 2 pipeline. So I just wanted to show you really quickly some of the things that we look for when we're actually doing our pulsar, when we're running our pulsar timing pipeline. This is pretty out of date, but I just wanted it to be like a little bit instructive so you can see what we're thinking about. So we use this YAML file setup. This is really nice. It's like a configuration file that is associated with each individual pulsar. And in that YAML file is where you change your settings depending on what you need to do. So for example, which parameters you actually want to be fit in the model, that's something that you dictate from the YAML file rather than directly in the CLAR file, like what I mentioned before. This is where if you need to manually excise time of arrival measurements, which we do sometimes need to do, this is where you would specify those. The changelog might be the most important thing that exists here because so many different people have their hands on these pulsars that we just want to make sure that like everybody knows what was done, right? Like we need to know why certain choices were made, why certain parameters were added or removed, and you just lose that knowledge over time. It's inevitable. Yeah, so this is where we specify the sort of configuration for any given run of the pipeline. And then we have this PDF output. This is specifically for PintPal, which is Nanograv's pulsar timing pipeline. Other collaborations have their own approaches to doing this, so it's not necessarily what everyone is doing, but this is very specific to Nanograv. So we have these PDF outputs that sort of show us whether or not the fit was successful. It shows us things like, hey, you know, every single TOA from this specific part of the data set was excised. What happened? You need to go look at what's going on. It helps us with version control. It shows like what versions of the different software packages that are used were actually used for that run. It shows you what parameters were fit, the quality of the fit, things like that. So it'll flag it if like the reduced chi-squared isn't close to 1. Yeah, this is the example of like every single TOA is being cut for this one specific kind of 430 megahertz part of the data set. So it's good to know if that's happening. Yeah, the versioning and everything. But then the thing that you're actually diagnosing are these residual plots. So that's kind of the main thing. You want to make sure that obviously you're not seeing sort of structure in those residual plots, which would be very unusual given that these are pulsars that have been timed for a very long time. But it does show you if there are TOAs that you should maybe think about excising. It shows you if there are problems in the fit overall. And sometimes it can be the case that there's an issue with just one, you know, front end, back end combination, and then you would need to address that specifically. It also shows the reason for which individual TOAs were excised. So that could be because of that signal to noise cut I mentioned. It could be, you know, because you manually kind of identified them as being, you know, needing to be cut. There are all kinds of kind of very in the weeds reasons why you would cut TOAs. And then you can also see the results of noise modeling here. So these are just the posteriors from, you know, measurement of red and white noise in the individual pulsar. And so you can make sure that what you're seeing is kind of reasonable, right? You're not pushing up against any priors, or the distribution doesn't look like totally ridiculous. And then we have some specialized tools for examining the data like up close and personally. So if you see some TOAs, for example, that are like really looking wrong in your residual plot, you can go through and you can look at the actual observation. You can look at the profile from that observation, and you can say, you know, is this just like some weird noise thing that happened and it didn't get flagged by algorithmic outlier excision? You know, are the data being like contaminated by something? Radio frequency interference is a common thing, and it just managed to slip through. And so we really, for anything that gets manually excised, we want to be very careful in identifying the reason for which it is being excised. So we want to go back to the level of data. Okay, and then I'll talk really quickly about what we're sort of up to in the future. This is the last section. So one really exciting thing that's going on is that Nanograv, and by extension, the International Pulsar Timing Array, is, you know, a big partner in the Deep Synoptic Array. It's funded by Schmidt Sciences, which is a private collaboration or a private organization that is launching 4 new observatories kind of all around the same time, which was announced not too long ago. It's a very exciting project. But the one that we're particularly interested in is the DSA. So DSA was originally called DSA 2000 because it had 2000 dishes. It no longer has 2000 dishes. They actually decreased the number and increased the size, which ended up being better for us in the long run. We get pretty good bandwidth with DSA. It goes from 0.7 to 2 gigahertz. And, you know, originally we were supposed to have about 20% of the time on Sky. We'll see what ends up happening. We have to write proposals for time and all of that. But it has better sensitivity than GBT and Arecibo. So this is going to be really powerful for us. We're really looking forward to this. Folks in the International Pulsar Timing Array also are thinking about the SKA, the square kilometer array. That's going to be revolutionary for pulsar timing, you know, kind of efforts. And I just wanted to like plug this recent update to the SKA science book that we did that describes kind of what a pulsar timing array would look like using the SKA. There's some delays going on with the SKA, and it's very complicated because there's buy-in from lots of different countries. And so it's always a little bit unclear exactly what the timeline is going to be, but once it's up and running, it's going to be pretty amazing. And that, like, if you've heard of the Meerkat Observatory, that's an interferometer in South Africa. That's a really amazing instrument, incredible collecting area. They get such good timing precision for their TOAs. That's like a pathfinder for the SKA, for example. So it's going to be that kind of a setup. Also, I already mentioned the ultra-wideband receiver that we're going to get. I just wanted to point out, I mean, you can see this integrated profile. It's not, since you can't see the scale very carefully, it's not that instructive. But it's pretty cool to be able to see the entire pulsar, or rather the pulsar over the entire band, from pretty low radio observing frequencies to 4 gigahertz. That's very cool, pretty unique. I mentioned Parkes has a similar system. But you can see that this is going to be really big for nanographs specifically. So you can see kind of like the frequency bands that we have available in our data sets with time. Technology has improved such that we can have this simultaneous observing band that's quite large. And that really improves our pulsar timing and improves our array in turn. Yeah, so that's all I've got. Thank you so much. And I'm happy to take more questions if you have them. Yes, we've.
Can you talk about the benefits that you made ultra wideband at the same time as like the DS frequency overlap with the ultra wideband receiver and like what kind of
Yeah, that's a fantastic question. It's actually a question that we have to think about a little bit when we're starting to plan the next few years of our observing program. So the ultra wideband receiver completely overlaps the frequency range that's available to DSA, but it's on the low end. So they have a similar low frequency limit. It's just that the ultra wideband goes much higher to higher radio frequencies. And so ultimately, because pulsars are these like steep spectrum emitters, it's good that that's where the overlap is, I guess, because the fall off happens at those high frequencies. But we have to think a lot about optimizing our timing. So there's not, necessarily a ton of benefit in observing the same pulsars with the same cadence using the same frequency range, right? So you do get much better sensitivity from DSA. It has much more collecting area, but we don't want to just be like repeating the same type of observing program. So one thing we've talked about, for example, is doing like a high cadence campaign using the GBT and doing that in addition to a more regular kind of monthly, every few weeks type campaign using DSA. And so we could be very strategic about the pulsars that we choose to do a high cadence campaign for that will kind of improve our sensitivity to continuous wave signals, for example. Yeah, so lots to consider there, but there is complete overlap and we don't want to do the exact same thing with both observatories. Does that sort of answer what you were asking?
Yeah.
Okay.
Okay, if you have more questions, then go to time. Let's get another round.
Great, so we have lunch set up at the back of the room. Levi can explain the various options there.
Rice, vegan, olive gobi, chicken, tikka masala, vegetarian, samosas.
Excellent.
So it's very. Yeah. And her, I was concerned about these and people. Okay. Yeah, you are. For a single star, yeah, but. Yes, it does. Yeah.
I know really. I was at figure two minutes. I cannot understand how we are, like, especially with the aliens thing, dude, like.
One thing to think about.
I also. Somebody's gonna have to do it. Yeah. Yeah, like I talked to the. Yeah, right. I'm getting the part. Why is it? So, at some point, I'm going to. Yeah, I will. I will. Yeah.
All right, everyone, you about finished with your crossword? I think everyone's working on it at halftime in the afternoon. Okay, we're starting back a little bit earlier since all right, so I'm gonna go through this work derivation on how to go from time arrival measurements that Thankful spoke about earlier to how gravitational wave influences actually change those arrival times and make impacts in our data sets. So this will probably take maybe 30 to 45 minutes, and then we can talk a little bit about what hack time looks like and how people should get organized into groups for mini projects. Okay, so first of all, you've probably seen this kind of expression before, but this might be new to some people. This is not a cosmological redshift or anything. This is meant to represent effectively a Doppler shift or a fractional change to the arrival rate of radio pulses from the pulsars. And we'll go through every single term here in detail. What we're looking at is a unit vector that's pointing from the Earth or from the solar system barycenter to a pulsar. And Roman indices will index spatial components, spatial directions. The omega here is a direction of propagation of gravitational waves. So it's starting from the source and it's pointing in the direction of propagation. That's going to be the negative of the vector that points towards the origin of the gravitational waves. So you might have seen this different ways around, but omega here will refer to the direction of propagation. And then P p hat again is just the unit vector pointing to the pulsar's direction. And finally, the most interesting bit, because these are really just directional response bits, the most interesting bit is the delta Hij, and that's a change in the metric perturbation. That is the change in the space-time metric caused by the wave. And as we're going to see, it's the difference between the value of that metric perturbation between what it is at the pulsar, a given pulsar, and what it is at the Earth. And the bit at the Earth is going to be the common bit, and the bit at the pulsar is going to be the not common bit. It's going to be dependent on the particular direction to the pulsar and the distance to those pulsars. So this might look like a very dry derivation, but we're going to go through it step by step because I think it's useful to know where this comes from. So we'll start off just with the most simple version of a perturbed space-time metric due to gravitational waves. This really is just the Minkowski space-time metric, the metric of flat space-time. But instead of there just being the delta Ij, dxi, dxj, we've got a very small perturbation here, Hij. That is the gravitational wave perturbation. And we'll always assume that that's very, very small. H is much, much less than 1. I'm also not putting any factors of G or C in here. We'll just assume those are set to 1. Okay, we can put them back if we ever want to translate to physical quantities again. And we're going to imagine that we've got our pulsar very nicely oriented just along the x-axis. We're at the origin of the coordinate system. Our pulsar is somewhere along the x-axis. And we've got photons, which are going to be representing our pulses, propagating along the x-axis and being affected by that metric perturbation. So we've got a null photon path toward the observer at the origin, and it's moving along the x-axis. Because we're looking at a null path, a photon path, then the value of the line element, ds squared, is just equal to 0. Okay, so we're setting the left-hand side to 0, and then we've just got minus dt squared, and because we're only along the x-axis here, the path is only along the x-axis, the second term collapses to 1 plus hxx. That is the value of the metric perturbation. You can think about it like a matrix, the value of that matrix that's in the xx component. Okay, all of these notes are going to be available afterwards, so if you don't get it, that's fine. We're just moving from here, then on to the next slide, where I've just moved the dx and the dt onto the other side of the equation. I've done a couple of things here, actually. So I've moved the dt over to this side. I've then divided the dt squared by 1 plus hxx. And because h is very, very small, whenever I divide by 1 plus hxx, that's equivalent to doing 1 minus hxx, okay? Because it's a very, very small quantity. And then if I'm taking a square root, again, that's just a leading order Taylor expansion. So square roots just show up as halves inside the small perturbation quantity. It's towards the origin. Okay, it's going in the negative x direction. It's starting out, yeah, from your perspective, it's starting out over here, and it's moving towards the origin of the coordinate system in the negative direction. Okay, next up, I'm just going to integrate over x, and I'll integrate over time here. So I'm integrating from an x that starts off at the pulsar and then goes along to the Earth. And that's just going to be minus the distance to the pulsar. The way we've set this up, that's going to traverse a distance to the pulsar, and it's a path that's going in the negative x direction. And then I take my integral, and I do that over time. And the pulse is starting off at some emitted time. So it's leaving the pulsar, and then it's showing up later at an observed time at our radio telescope on Earth. So I've just got my negative there, which is outside the integral, 1 minus hxx, and I've got t prime as my integration or my dummy variable for integration purposes. Feel free to interrupt me if this is not clear. Maybe you've seen this before. probably true for some of you. If not, then stop me if anything here is not quite clear. So we haven't done anything very fancy at the moment. We've just taken the simplest form of a gravitational wave spacetime and written down what the line element is for that perturbed spacetime, and then imagined a setup where we've got photons propagating in a certain direction inside that perturbed spacetime. And that is representing our pulses moving through some kind of perturbed spacetime caused by gravitational waves. Okay, so I've been able to do the left-hand side of the integral. That's just minus the distance to the pulsar. Again, this, this would normally have a factor of c in here, but I'm leaving out c. That's just equal to 1. Next up is I just rearrange this. I've got my distance to the pulsar. I can put that out on the left-hand side. And then I've just got a factor here that's 1. So I can just rewrite that as minus T obs minus T emitted. And then the only thing that's left over, the explicit integration that I have to perform, is over the HXX. Okay, this term, the 1, is something that's easy for me to do. So rearranging and kind of massaging the terms of this equation a little bit, I've got L, the distance of the pulsar, is equal to the observed time minus the emitted time. And then there's a little bit extra here that's caused by the gravitational wave perturbation. Without any gravitational wave perturbation, this would make total sense. Because if I had a factor of c in here, that's just telling me that the light travel time to the pulsar is L over c. Okay? Everything good? Think about that. So all of the gravitational wave effect is wrapped up inside that the final term there. Now, I'm going to generalize this a little bit because the final expression that was actually on the first slide, it had directions to pulsars in arbitrary directions. It also had gravitational waves propagated in arbitrary directions. So I'm taking the very specialized setup that I had, where it was just my pulsar was nicely oriented along the x-axis, the photons were propagating in the negative x direction, and I'm just going to rotate the coordinate system to be arbitrary. So now I've got a pulsar that's in some direction, unit vector p, and a gravitational wave is propagating in some other arbitrary direction, omega. And to do that, I just change my hxx to be pi, pj, hij. So this is the arbitrary three-dimensional spatial part of the metric perturbation. Remember, Roman indices here, ij, are over spatial indices. And the reason why I've got the pi, pj is that I'm projecting that metric perturbation onto a specific direction, pi, pj. So if pi really were 1, 0, 0, that is entirely along the x-axis, then that would pick out the hxx. But I'm shifting to be more general. So the final expression I get holds for any pulsar in any direction. All right, so using that, I'm just replacing the expression I was ending with on this slide. And I'm replacing the hxx with the pi, pj, hij. And that simply gives this expression here. I've massaged the expression a little bit. So I've brought the observed pulse time, or the observed photon time, to the left side of my equation. And I've written that in terms of the time at which the photons were emitted, plus some nominal light travel time, which is going to be L over c, distance to the pulsar divided by c. And then I've got this additional little bit, this perturbation caused by the gravitational wave. And I've put in now explicit expressions for the endpoint, the starting and end point of that integration. So you'll notice before I would have had T emitted and then T observed. But in my integral here, I've approximated that T observed is roughly equal to T emitted plus the light travel time to that pulsar. Okay, it's fine. If I were to not make that expression, or not make that approximation, it would eventually be somewhere where it would lead to a higher order term in the kind of redshift of the arrival rate of the pulses, and I would be able to drop that off. So I could just make that approximation now, and it's fine. So T observed is equal to the emitted time plus the light travel time to the pulsar, plus a little bit extra caused by the gravitational wave effect, where the endpoints of my integral are T emitted and then T emitted plus the light travel time. So what I'm doing is I'm effectively integrating over the entire metric perturbation influence from when the pulse leaves the pulsar to when it finally arrives at the Earth. And this the metric perturbation has some dependency on the time at which I'm looking at the metric perturbation, and then where my pulse is along the metric perturbation at any given time. Okay, so the pulse is moving through that perturbed space-time. It's picking up the influence of that perturbed space-time as it's moving along. So I'm building in that sort of time and spatial dependency in here, because this would be T, and this would be the spatial part of the metric perturbations dependence. And again, this is just my integration variable T prime. And this holds for pulse number 1. So this is my expression for the first pulse that I'm recording. It leaves the pulsar, it travels, it's picking up the effect, and then it's arriving at Earth. But when we're timing pulsars, we have no real absolute reference scale for when these pulses should arrive. We're looking at the difference between the arrival times of the pulses, and we're comparing that to our models. So I want to be able to write down an expression for the influence on the difference in the arrival rate of the radio pulses. Nominally, the difference between one pulse and the next pulse should be the instantaneous measure of the rotational period of that pulsar, right? Because you get a flash, and then it spins around, and you get a flash again. So this is my expression for pulse number 1. Now a second pulse, it should just be one period later. So if I take my T primed emitted, that's going to correspond to the emitted time of the second pulse. That should just be the emitted time of the first pulse plus one rotational period T. Now that's not going to be the same as T prime observed minus T observed, because as that pulse has propagated, as that second pulse has propagated, you've picked up a little bit of an additional effect, right? So the difference in the emitted time of the second pulse and the first pulse is just P, but the difference in the observed time of the second pulse and the observed time of the first pulse is the rotational period P plus a delta P, and that delta P is the gravitational wave effect. It's an apparent shift in the rotational period of the pulsar caused by the photons from the pulsar moving through the perturbed space-time. So I'm not actually changing anything about the physics of the pulsar. I'm not actually changing the rotational period of the pulsar. It's an apparent change in the rotational period of the pulsar, an apparent shift in the rate at which these pulses are arriving. So I'm going to do a redefinition here. It's just a redefinition of the integration variables for time. It's not that important. It's something for you to follow along later if you try to redo this this derivation. So don't worry about it too much now. But this is what my expression will look like if I take the difference in the arrival time of the second pulse and the arrival time of the first pulse. It effectively looks like I'm taking the difference of a term that looks like this for the first pulse and another term, a corresponding second term for the second pulse. So if I just take the difference in those expressions for the different pulses, I get T primed observed minus T observed. And that should be P, but then I've got my additional gravitational wave bit. We're now inside my integration. I've got two metric perturbation bits. I've got a metric perturbation at some time that's corresponding to the second pulse. So it's like T primed plus P. And then it's subtracting off the metric perturbation at the time of the first pulse. And that's one rotational period behind the first term. Okay, difference in two metric perturbations here, integrated over the light travel time between the pulsar and the Earth. So without gravitational waves, this looks and makes total sense. I wouldn't have the second bit here. I would just have T primed obs minus T obs is equal to P. Yeah.
From your first definition of T prime minus T, is that saying the whole thing after the plus minus delta P, or just the thing that's inside the interval?
This thing here is the delta P. So it's the perturbed bit. So this delta P corresponds to this entire thing here. And then I've got the usual P that's to the left of that. So I'm trying to write things such that delta P is only the anomalous extra bit that's caused by the gravitational waves. And note here, I haven't said anything about what kind of source I've got for my gravitational waves. I haven't even said if it's a monochromatic wave or it's a burst or it's a stochastic background. I don't need to specify yet. It'll help me make my expression more compact at the end if I take a particular form for the gravitational wave, but I don't need to do that quite yet. Levi?
Yeah, I know the context that we're doing Vanderbilt gravitational waves, so the metric shouldn't change between one pulse and the next, but I don't know, like, if we had a clock that we knew wasn't change, pulsars have noise that we can't know, but if we had a clock that was better, or, we knew the noise property better, could we detect these gravitational waves between the pulses, or gravitational shifts between pulses?
When we effectively, so the question is, we're looking at gravitational waves of such long period, long wavelength, that we shouldn't be able to be sensitive to these small changes in what the metric perturbation is between one pulse and the next. But could we in principle? And what I'll show you next is that we can, that's what we're leveraging here actually. And what we're doing effectively is taking account of and using the separation of timescales that you just mentioned, right? Because we're looking at pulsar rotational periods that are of order milliseconds, but we're trying to measure gravitational wave effects that are of order, not milliseconds, but more like, 10 to the 4 to 10 to the 5 seconds and beyond, year to decade timescales. So we're going to use that separation of timescales, the fact that the rotational period P is so much different from the gravitational wave timescale, that we'll be able to make some approximations in what happens from T primed to T primed plus P. In fact, that's one of the next things that I'll do here. Okay, so we're going to do a first order Taylor expansion. We've got P here is of order milliseconds, and then the gravitational wave period is 1/nanohertz. That's obviously of order 10 to the 9 seconds. 1 nanohertz corresponds to 30 years approximately. So we've got a very clear separation of timescales here, which means that I can just expand my metric perturbation, expand my gravitational wave metric perturbation into what it is at a given time, T primed, and then just do a linear expansion of that. So the gravitational wave metric perturbation at T primed plus P, that is one rotational period of the pulsar later, is just what it is currently at T primed plus partial Hij with respect to T primed. And then the time scale here I put on the end that I multiply this partial derivative by is just the rotational period of the pulsar P. And that's a perfectly fine approximation for what we're dealing with. The time scales are so different that this kind of approximation is not affecting any of the data analysis or searches that we do for gravitational waves. Okay, we've got 10 to the 12 order of magnitude difference in P and the gravitational wave period. Okay, this makes my expression a lot easier on the previous slide because I had an Hij term on the previous slide. I've expanded out this Hij T primed plus P, and that becomes Hij at T primed plus the first order expansion term, which is the partial derivative term. And then I'm subtracting off what the metric perturbation was for the first radio pulse. That means I just get rid of the absolute value of the metric perturbation at that time. And I'm left with this expression that looks like just an integral over the partial derivative of the metric perturbation with respect to time integrated over time. Okay, and I've done a little bit more light rearranging of this expression so that it looks like an apparent change, an apparent fractional change in the rotational period of the pulsar, where the delta P is sourced by the influence of the gravitational waves interacting with the passage of the photons.
That we can change after each period, right?
So the question is, can Hij change after each period of a pulsar? Can it change on that time scale? Yeah, it can change, but we're saying that the gravitational waves that we're looking for and that we're very sensitive to are the ones where the variations are small. And they're small to the point where I'm not expecting changes in the gravitational wave emitting system of order milliseconds. We're not looking at the physics of those kinds of systems. We're looking at the dynamics of much larger systems where the dynamical timescales are more like of order 10 to the 7 seconds or 10 to the 9 seconds. That's why we're able to get away with this approximation. Okay, so we're almost there. I've only made a couple of assumptions and a couple of approximations along the way, but this is mostly just the kind of thing you would do in a GR class, which is write down a metric and then look how photons propagate in that metric. Okay, and I've made a few approximations along the way. And then if I just make this kind of simple definition that the apparent fractional change in the rotational period of the pulsar can be related to fractional change in the arrival rate of radio pulses, right? That's just saying that a pulse should arrive every rotational period of the pulsar. So I can equate an apparent change in the rotational period of that pulsar to an apparent change in the arrival rate of the radio pulses I'm getting from that pulsar. So I'll call this is not a radio frequency. This is a frequency in the rate of arrival of pulses. So this is how often I'm getting a pulse. Don't confuse that with anything related to the radio frequency or the observation frequency of those radio signals. It's just, I've got pulses arriving at a certain rate. And I'm going to call that Z. That's going to be my Doppler shift or my apparent shift to the arrival rate of those signals. And now to make the algebra a bit easier, and so you can see a separation of terms, I'm going to substitute in a monochromatic gravitational wave. So that means that I'll take a particular form for my metric perturbation. This is the first time that I'm being explicit about the form of that metric perturbation. I'm going to say it just looks like a monochromatic wave, so it's got a cosine that deals with the propagating wave bit of that. It's got a certain angular frequency, omega GW, and it's propagating in a certain direction, which is uppercase omega. That's the omega that I showed you in the very first slide. And as usual, angular frequency is just 2 pi times the usual frequency we talk about. And then to deal with all of the kind of metric-y bits of this, I've just got a metric amplitude, uppercase Aij, which has some kind of directional dependence. Now, this might seem like it's a very constraining assumption. Not all gravitational waves look like they're monochromatic waves. And that's true, but I can always do a plane wave decomposition of a gravitational wave signal. I can always decompose any kind of signal that I've got into a sum over waves that look like this. So it might not hold for every single specific signal, but I can always reduce any signal down to sums of terms that will eventually look like what I show you. So let's take that metric perturbation form and drop it in. And what flops out of some, additional 1 or 2 lines of algebra that you can do is this final expression for the apparent Doppler shift to the arrival rate of the radio pulses coming bigger pulsar. And it's nice, you get this separation of 2 important bits of this expression. This is the half PIPJ over 1 plus omega dot P. That is everything to do with the angular sensitivity or the angular response of a given Earth pulsar system to gravitational waves. Okay, so that whole term in there would eventually be related to things like uppercase F plus and uppercase F cross. Those are the antenna response functions for a particular gravitational wave experiment. And I would get my uppercase F plus and my uppercase F cross if I just broke this down into kind of terms that depend on and are linear combinations of the plus and cross polarizations. I can tell you right now that this expression here, combined with a polarization basis tensor, the EIJ plus and EIJ cross, that is just uppercase F plus and uppercase F cross. Those are just the antenna response functions. But the most important part of this is that I get a separation of these gravitational wave effects. I get an imprint of the metric perturbation at the Earth, so the kind of the endpoint of the integral, and I get an imprint of the metric perturbation from when the pulses started at each pulsar. And that is unique to gravitational wave experiments. The fact that we've got such a large experiment and a lot of the influence of the gravitational waves kind of washes out in the middle of that experiment. We're just left with imprints of the endpoints of the integration of the photons propagating throughout the space-time. That's really special. If you see LIGO, if you see LISA, other kinds of gravitational wave experiments as well, they're all related to kind of local measures of the gravitational wave field. What we get is a local measure at the Earth, but also a measure of what the metric perturbation was like when it washed by each pulsar. The reason why this is special will become really explicit next week when we get on to trying to measure and characterize continuous wave signals from individual supermassive black hole binaries. But as a little teaser right now, this allows you to see into the past history of the gravitational wave emitting systems. What this is telling you is information about what the gravitational wave was like, and therefore what the source was like some time L over C in the past. The distances to the pulsars that we monitor are of order hundreds to thousands of parsecs. I mean, they're all in the Milky Way, but that's the kind of length scale over which we're looking at these pulsars. And that means the light travel time is of order hundreds to thousands of years. So even though we're looking at pulsars and we're only really recording data on those pulsars for years to decades, we still get a little phantom record of what the gravitational wave emitting system was like thousands of years ago. Some people have phrased this as like temporal aperture synthesis, because you get imprints corresponding to different dynamical states of the system. Even though this looks like L here, that is L for a particular pulsar. We've got different distances to different pulsars. So if you can collect up all of these records and you have accurate enough measurements of the distance to those pulsars to be useful, then you can reconstruct how much this system was evolving over thousands of years, even though we're only looking at a tiny, tiny sliver of the system, over 10 to 20 years. That's really, really cool, I think. It's very, very hard. As anyone who in the room has tried to search for continuous waves or model continuous waves, we don't have pulsar distances that are anywhere near good enough to leverage this at the moment, but it is the dream. And it is the promise of having terms that separate like this. And that's pretty much what I wanted to show you. I'll move on to the interactive demo next, which you can play with yourself. I want to show you how you get this directional modulation of the gravitational wave effect. Basically, if you have a gravitational wave source that is directly behind a pulsar, you get no impact whatsoever on the arrival times of the pulses. And likewise, if you've got a gravitational wave source that is on the opposite sky to a pulsar you're not, then again, you get zero effect. But the reason why you're getting zero in both of those cases is quite different. So I'm going to move on now to one of the interactive demos that I've created that you can look up and play with yourself. But are there any questions about any of the steps here in the math? Yeah, Lucas.
I was curious about the measure being on watch in between. Is that kind of a relative or approximation of the time between pulses? Was the time scale approximating
Yeah, so the question is this resultant effect that a lot of the behavior between the Earth and the pulsar washes out, and is that an artifact of the separation of timescales? It is, and it's also a consequence of yeah, actually it's more of a consequence of the fact that we get many, many wave cycles between the Earth and the pulsar. So you think the gravitational wave periods are of order years to decades. That means that the wavelengths themselves, if you just quickly work this out, would be of order parsecs. And the distances to pulsars are more like hundreds to thousands of parsecs. So we get lots and lots of wave cycles that are propagating between the pulsar and the Earth. Again, that is sort of different from other kinds of gravitational wave detectors. In LIGO, the gravitational wavelengths are more like the size of North America. They're comparable to the size of the Earth. And so influences that are happening between Livingston and Hanford are somewhat similar, and they're spanning approximately the same wave cycle. LISA is kind of in an in-between mode because at low frequencies in the LISA band, the waves are longer and larger than the size of the 3-satellite constellation. But then I think it's at roughly 20 millihertz in the LISA band. 20 millihertz corresponds to the frequency at which you would start to get wave cycles inside that constellation. And that shows up in the LISA noise sensitivity curve. You start to see at higher frequencies wavelength wiggles and modulations. That's because the mode of the detector is changing, and the expressions for the antenna sensitivity, the directional sensitivity are changing as well. So LISA straddles both long wavelength and short wavelength approximations. That's just the terminology for how we refer to the mathematics of the antenna sensitivity. In LIGO, you're in the long wavelength approximation. For PTAs, we're in the short wavelength approximation, where short just means short relative to the length of the detector. Okay. Tejas?
How did it get to denominator? 1 plus 9.
Yeah, so you'll notice over here, I had to do a derivative and then an integral. And when I substituted in my my monochromatic gravitational wave form, I pull out eventually something that I can collect together to get the 1 plus omega dot p. So it's a consequence of doing that integration over time. It pulls out the 1 plus omega dot p.
Take out the HIJ, is that not possible? It's just a
No, it seems like that you're doing a derivative and then you're doing an integral. But I encourage you to try it yourself. it leads to that expression falling out in a non-trivial way, okay? So it seems like you would get nothing, it would just cancel out. But you do get the additional 1 plus omega dot p falling out.
Okay.
That's a homework problem.
And I'm a little confused as to what the units of L are. Like
The units of L
Yeah, is it just the full thing? Like, is that midline?
doesn't matter. It's so L is a distance to the pulsar, but I'm writing every distance as time, and I'm writing every time as a distance because I've set c, the speed of light, to be equal to 1. If I was going to start calculating physical quantities and putting in numbers, then yes, I would put in factors of c, I would put in factors of g for Newton's constant. It's not necessary here. But if you want to think about L having a value, L has a value that is of order kiloparsecs, which is thousands of wavelengths, and the wavelength here is of order a parsec. So all right, so that's the final expression, which is what I showed you on the first slide. You've got the angular sensitivity bit, and then you've got the actual metric amplitude bit, the delta Hij. Now, as another little bit of information, and we'll get onto this later in the week probably, this denominator term is the sole reason why the Helms and Downs curve is asymmetric. This gives a preferential sensitivity to gravitational waves propagating in a certain direction with respect to the orientation of the pulsars. So this denominator is why we've got a Helms and Downs curve that starts off at a certain value, close to 0 angular separation between the pulsars, goes negative, and then becomes positive again, but it doesn't return to the value it had originally. It goes back to the half the value it had originally. And that's because we do have some preferential sensitivity to the gravitational wave signals propagating in certain directions. All right, so let me get out of this now and turn on to the demo. Yeah.
You stated we have a direction. So, direction. What do you mean by that? Like, is that it's not a sensitivity on our part, right? It's an astrophysical. It depends on the relative position of the gravitational wave.
Exactly. Yeah. So the question was, what does it mean for us to be more sensitive to gravitational waves propagating in certain directions than others? And really, that is a statement about the entire Earth pulsar system. So we're on Earth, we're looking at a pulsar in that particular direction, and that sets up our coordinate system for saying I'm more sensitive to gravitational waves that are coming from that direction than that direction, okay? And that's true for every single pulsar location in the sky. There is a preferred direction. When you correlate them together and integrate overall gravitational wave directions in the sky, you get the Helms and Downs curve. And that gives you more sensitivity to kind of gravitational wave signals that are close by that collection of two pulsars. And that adds up to be positive and greater overall than if we had correlated two pulsars that are almost opposite on the sky. All right. Well, let me show you this, and maybe that'll be clear. Okay, so you look this up yourself. It's maybe going to look a little bit flickery on the screen. Okay, so this is the basic setup. I've got some gravitational wave source that's very, very far away. And then I've got a pulsar here that's sending out a regular train of pulses. This is not what it looks like. This is just a toy demo. But you've got this regular train of radio pulses that in our detector looks like a pulse every rotational period. Now, as I move this gravitational wave source around in the sky, so it's transiting the Earth pulsar line of sight in different ways, you'll notice that the observed pulses are slightly departing from the idealized form. So I've got my idealized form here, which is in the kind of phantom faded gray in the background. And then I've got my actual observed train of radio pulses, which are brighter in the bright white. So if I move this source around in the sky, you'll start to see that there are variations in how much the observed pulses are departing from their idealized train of radio pulses. But something really weird happens when I move the gravitational wave source to be kind of coinciding with the direction of the pulsar. Let me bring this up here. If I reduce the angle between the gravitational wave source and the pulsar, it seems like it's quite large, and then all of a sudden snaps to zero. At this orientation, the pulses are surfing, and that is the terminology that is used. The pulses are surfing on the gravitational waves, and there is no difference in the phase of the Earth term and the phase of the pulsar term. Okay, they just cancel themselves out. So there's no resulting influence to the arrival times of the radio pulses. Okay, so what we've got here is destructive interference between those two components of the gravitational wave effect. We've got destructive interference between the Earth term and the pulsar term. So there is no net change to the behavior, to the arrival rate of the radio pulses. But this is a very, very fast changing effect on the sky. It's highly oscillatory. These interference fringes between the Earth term and the pulsar term are so thin. We're talking of only maybe a degree or so. So that if I change this angle even a little bit, I get a huge effect. And as I'm moving this around in the sky, there'll be an overall envelope to the effect, but there are also highly oscillatory changes. And that's not going to be apparent until we go through the derivation, probably sometime early next week. But I get this overall envelope effect. You'll see in the bar along here, we've got highly oscillatory behavior. Constructive and destructive interference between the different Earth terms and the pulsar terms. Let me bring the gravitational wave source around to the opposite side of the sky from the pulsar. And you can see we're basically already down towards zero again. In that way, the kind of envelope term that controls the angular sensitivity is the thing that is actually causing the zero over here when the gravitational wave source is on the opposite side of the sky. So in this way, the reason why I've got a zero and I've got no net effect in this scenario, that's entirely due to the antenna response term, that half pi pj over 1 plus omega dot p. So that's just the directional sensitivity I've got in my Earth pulsar system. And the reason why I've got a zero in the opposite sense is wave interference. That's interference between the Earth and the pulsar terms. So they're very different reasons. The net effect is the same, but there's different physics that's causing these zeros, and there's different physics that's causing my zero at zero separation and 180 degree separation. If we were able to know the distances to pulsars very well, then we could leverage this kind of very sharp change going from zero to slightly offset to localize gravitational wave signals super well in the sky. We'd be able to get kind of sub-degree squared localization regions for searches for individual sources of supermassive black hole binaries on the sky. Unfortunately, we don't know the distances well, and so we can only really make use of the overall envelope behavior caused by, this slower change. It's more like a cosine change in the angular response. Liana? Say again? So the question is, why do we not know the distances that well to pulsars? There's one pulsar that we know distance to quite well, and that's known to about 0.1 parsecs. And that should be good enough in principle for us to leverage this kind of interference effect. But that is the closest pulsar that we monitor to the Earth. Every other pulsar is obviously farther away, and there are only a certain number of pulsars that we can use timing parallax measurements to get the distance to the pulsar. So timing parallax is what you would do for the nearest by pulsars, and that usually gets the highest precision. And then as you get farther away, you have to use things like, I think Thankful mentioned this earlier on, you make an argument based on the amount of dispersion behavior that shows up on your pulses. So you look at the dispersion behavior of your radio pulses, and you interpret that as caused by interstellar dispersion. You take an electron density model of the galaxy that applies along the line of sight between you and the pulsar, and you invert that to get a distance. That's entirely dependent on your electron density model of the galaxy, though. And the distance uncertainties are of order tens of %, I think. Now, people play other kinds of games to get more precise distances to pulsars. Timing parallax is good, but what is even better, and what gets you down to the very small measurement precision for that nearest by pulsar, is that people have been able to model interstellar scattering screens and the behavior of plasma relatively close to the pulsar to measure precise distances. So you're looking at higher order scattering behavior, higher order like interstellar medium effects, and you're working at the geometry of the pulsar, the Earth, and then plasma scattering screens. And that's how you do it. But you can only do that in high signal to noise scenarios, which applies for this closest pulsar to the Earth. Whether you can do that on a more industrial scale is unclear. Likewise, VLBI, which is a very long baseline interferometry, people have tried to do that to get more precise parallax measurements of pulsars, but it hasn't really improved much. Other things that people have done is take like Gaia data sets and look for companions and use Gaia to try to measure distances to pulsars. That's not very competitive, and it's only applied to, I think, a small number of systems. Yeah, Kat.
Great. What does this edge effect have? What are the implications of that on if we're observing a binary system or trying to observe the gravitational waves from a system, because then it is its own source?
So the question was, so if you've got a gravitational wave system, a binary system that is generating gravitational waves, could that act like its own source and affect? Oh, do you mean like a pulsar in a binary system?
Yeah.
That is itself generating gravitational waves and affect them? It's interesting. Yeah, that is a super interesting idea. The timescales would be different again, though. I think they'd be closer in timescale because you get pulsars in binary systems that are more comparable to like days and months. Thankful. What are the typical binary periods of pulsars? Can you get very long, very short? Days. So days are still much, much longer than the milliseconds that we're observing the flashes of the pulses. So you get this separation in scales, but we also, the gravitational waves coming from those pulsar binary systems are fairly weak. And the system is far enough apart that, the gravitational waves are very weak. And we can only measure those gravitational waves at the moment indirectly through things like the Hulse-Taylor binary. But do you mean, could it like?
I guess I'm the binary system.
Mhm.
Would the gravitational waves just appear to briefly disappear when they pass each other? Because they're running along one side and then appear again?
It's interesting. Would the gravitational waves appear to briefly disappear? And again, the gravitational waves are coming from this pulsar binary system. I don't know, because usually it's very interesting. I'm not even sure you can describe what the gravitational wave behavior is well in that scenario, because usually you have to get out beyond several wavelengths to what's beyond what is called the wave zone, because what's happening here is very nonlinear, very highly dynamical. I'm not sure if you would get a complete like cancellation or what it would look like. I have to think about that some more. It's interesting. Yeah, so
Here, like if say that we have just 1 gigabytes of data and we're trying to understand what that possible. So is in this case, there will be no memory effect, or is this very small memory process is fine?
the question was, would there be no memory effect that would also help us and maybe pick out what behavior has been over long time scales? The memory effect is pretty small until you get to the merger and post-merger phase of the system. So it ramps up very quickly, but we're nowhere near merger. Like for most of our systems, they are millions of years before merger, and they'll merge at frequencies outside of our range of sensitivity. They'll merge towards the lower edge of the Lisa band. Now, the memory effect is one way that we can be indirectly responsive to the merger phase, because it is a low frequency signal. It's a step function approximately in gravitational wave strain, which when you convert that to time residuals, and that's something I didn't actually say on the slide, in order to go from the apparent Doppler shift to the arrival rate of the radio pulses to an induced timing effect, you take that Z and you integrate over time. That converts it into like timing residual, the induced effect on the arrival times of the radio pulses. When you integrate a step function in strain over time, that turns it into a ramp. And that is a low frequency signal that could show up in our pulsar timing data. So we have people that search for gravitational wave memory effects as indirect signatures of mergers. There are other things that can source memory like that, but the merger phase of a binary system is the most common. Now, a ramp can show up due to other things as well. So an apparent memory effect can show up in other ways just due to pulsar glitches, which can look like a sudden change in the rotational period of the pulsar, which when converted to residual space looks like a ramp. But it's usually a glitch. A glitch usually causes the ramp to look like a certain sign of a ramp, whereas a memory effect will be plus or minus modulated depending on the orientation of the direction of the signal compared to where your pulsar is in the sky. So you get a directional effect that can help you in principle discriminate memory effects from pulsar glitches. Okay, so this is basically the geometry of what's going on here. I encourage you to go and play with yourself, play with this yourself. You can change the frequency, the strain amplitude. You can switch on the plus, cross, or both modes of gravitational waves. You can switch on wave fronts, which starts to look a little bit funky. You can add the test ring. So this is a ring of test masses. So you can see the influence. Let's get rid of this. You can see the influence of a gravitational wave that's propagating along this direction shown by the green arrow. And if you put a ring of test masses in this part of the sky, how would that ring of test masses respond to the gravitational waves? And in this sense, because of the way we've got this oriented, we're seeing an elliptical polarization of the gravitational waves, a combination of the plus and the cross. So you get this kind of weird jiggle. Yeah. Now, again, this has nothing to do with the source of gravitational waves. To take you on to the source of gravitational waves for binaries, that's something we'll study towards the end of this week and the start of next. But here's a little teaser. If this loads up. Or if it doesn't, you can play with it yourself. There are several demos on here. But the demo that I'm trying to get onto right now is one that has gravitational wave coming explicitly from a binary system and then propagating. Yeah, oh, that's the first one. Yeah, that's the first one. Yeah, that's the purple one here. This one actually has gravitational waves coming from a binary system. You can change the orientation of the binary system so that we're responding to both plus and cross polarizations coming from it. Or if it's only edge on with respect to our line of sight, you only get the plus mode of gravitational waves, so it's linearly polarized. And all of these different effects, and even the distance to the pulsar and how that's impacting the frequency of the gravitational wave signals that we're picking up, all of that superposes in really interesting ways. So that should give you more of an intuition for the different signals that can show up But again, that's more relevant for continuous waves when we look at that next week. All right, I think I'll leave it there unless there are any more questions, but I'm happy to keep talking afterwards. It just showed up. There we go. So here's my pulsar over here. Here's my source. I can move my source around in the sky. I can move my pulsar relative to the Earth. And if I move my pulsar relative to the Earth, it will change, it will modulate the signal because I start to get these different directional projection effects between the gravitational wave source. The gravitational waves are coming out of that binary system and then interacting in different ways with the Earth pulsar system. So go and play with these demos yourself. If you have any questions about the math or anything that we've gone through, let me know. Otherwise, we'll take a little break. We'll come back in 15 minutes and talk about the mini projects. All right, thanks. All right.
Yes.
Mini projects. What does this mean? What are you expected to do? What should you have at the end of the 2 weeks? All of this is pretty much a choose your own adventure. The way we've done this before is that the organizers have created some ideas that at least, you know, either you're attracted to the ideas and you want to explore those ideas, or you know you don't want to do those things and you come up with your own ideas. What we've tried to do here is just create a series of possible explorations that you could make reasonably over 2 weeks. Now, there's no need to try to turn this into a paper at the end of 2 weeks. There's no expectation that you'll have paper-ready publications after 2 weeks. But what you could have is the kernel of something that turns into a paper that or at least things that you explore and follow up with your summer school colleagues on. I think the first time we did this 4 years ago, we made quite a bit of progress on some of the projects, and those could have turned into projects, could have turned into papers, but people went their own way and had their own research topics. So there's no expectation this leads to something, but the intention is that you work with some people at the summer school, you get to know each other. Within a group, you might be interested in the same thing, but you could have different strengths and different, expertises. You come from different, expertise, whether that's on pulsars, whether that's on gravitational waves, maybe that's on supermassive black holes. Maybe you're a strong programmer. Maybe you're stronger on kind of the theory. That's great. Having a diverse expertise kind of reservoir is great in these kinds of groups. So what we've got here are different possible projects. These were just some things that I thought could be interesting and you could try to tackle. Minimum number of single sources consistent with the nanograph 15-year results. I said nanograph here, but that could be any of the pulsar-timing array results that came out several years ago. And there it's really, the Hellions and Downs curve is what you get on average with many, many sources. But our uncertainties on the cross-correlation measurements are still large enough that it's reasonable to question how many sources or how few sources you could have in the population of supermassive black hole binaries to still look like the Hellions and Downs curve. And it's up to you whether you decide that question is based entirely on the Hellions and Downs curve, or is that also based on the spectrum. Now, we've only got of order 5 frequencies in the spectrum that are actually well constrained and agreeing well with the Hellions and Downs correlation pattern. So does that mean you need just 5 single sources? Could you have some eccentric sources that are spread over different bins? These are like extensions to the question, but to lead in order, can you get something from a few single sources that looks like the Hellions and Downs curve? That's a reasonable question to ask, I think. This one, very open-ended. This is what kind of machine learning things, tools, approaches can you tackle in pulsar-timing array data analysis? I think the first thing you should answer is, what do we actually need machine learning for in PTA data analysis? Machine learning is this amazing hammer, and people are constantly searching for a nail to hit with that hammer, but sometimes it's not necessary. And we've got pretty good methods that can do pulsar-timing array gravitational wave searches in more traditional senses. But there are lots of things that machine learning is useful for, and it's up to you to explore how you would do that. One possibility is simulation-based inference. Simulation-based inference is a description of techniques where you never explicitly calculate a likelihood function. The likelihood function is usually the statistic that you're using to optimize and fit sets of parameters. At the very basic level, fitting your likelihood function is kind of like minimizing your chi-squared. You're fitting parameters. But sometimes that likelihood is difficult to evaluate, it's expensive to evaluate, and in simulation-based inference, what you do instead is you just generate data lots and lots of times, and you see how well your observed data set matches kind of synthetic data sets that you're able to create yourself. And in that way, you optimize what has generated that synthetic data in the first place. Another variation of this is variational Bayesian inference. And in variational Bayesian inference, that's a bit more difficult to explain as I'm standing up here, but the idea is that a lot of what we want to do is learn the posterior probability distribution of parameters. The posterior probability distribution is Bayesian speak for an uncertainty spread in some parameters that are consistent with data. And that posterior probability distribution is unfortunately not often from a standard family of probability distributions. It's not usually a Gaussian or some other standard distribution. In variational Bayesian inference, you try to fit families of distributions to your posterior. And in that way, because they belong to a standard family, you're able to draw samples very, very quickly and efficiently. So variational Bayesian inference has now been coupled with machine learning to use things called normalizing flows to be the standard distribution that you're able to draw samples quickly from. So that's another possible angle, but it's up to you what you explore there. 3, the distribution of Fourier coefficients versus the Gaussian assumption. This will probably become more clear tomorrow to everyone, but usually when we're describing the statistics of a gravitational wave background, Gaussian is one of the first assumptions we make. And that just means that you can describe everything you need to know about the stochastic gravitational wave background by looking at the variance of the Fourier modes. So you only need to look at the mean, but the mean is 0 by definition, and the variance. And within the variance, you can describe things like the stationarity of the signal, the polarization of the signal, and the level of anisotropy or isotropy of the signal, and the power spectrum, things like that. However, over the last several years, people have started to wonder, if I've got a population of supermassive binary black holes, discrete systems, and there might be some finite population effects that are sourcing my signal. It's not just a continuous distribution of these binaries. You can't get half a binary. You can't get a quarter of a binary. The minimum number of binaries you can get is 0, and the next is 1. Okay, finite population effects could be affecting our signal. And in that sense, what will that look like when we look at the statistics of the signal? So that could show up as non-Gaussian effects on the distribution of the Fourier coefficients. Number 4, single source localization. People that are interested in exploring this, I've got a Fisher framework that's set up from a recent paper that I wrote. And it's interesting to go from Fisher localization estimates, which are very fast, efficient, to Bayesian analyses, which are completely correct, but can be slow. Fisher is fast, but an approximation. Bayesian is accurate, but slow. Can you work out some kind of calibration factor that allows you to, find a relationship between those different quantities and then bootstrap your way to getting quick Bayesian estimates based on a Fisher estimate that you multiply by some factor? That could be interesting. Precision growth as a function of time. This would be things like if I take a long synthetic pulsar-timing array data set and I chop it into time slices, then how is the precision on the amplitude and the spectral index of the gravitational wave background changing as a function of time? What does that look like? And therefore, given current levels of precision, can we forecast based on number of pulsars, based on the amplitude of the background, et cetera, what it's going to look like down the road? If you want, a little bit of this idea was touched upon in a paper led by Nihan Paul in 2020. The paper starts with astrophysics milestones. for pulsar timing arrays. But seems like no one's interested in that, so we don't need to worry about it. And the last one that we've just generated as an idea is the evolution of the optimal statistic p-values via the generalized chi-squared distribution. The people from OSU will have heard generalized chi-squared distribution probably more than you thought you wanted to, because Jeff Hasbun wrote this great paper a few years ago, which was the first kind of proper formalizing of the idea that the null hypothesis for the gravitational wave detection statistic, which is the optimal statistic, doesn't obey a Gaussian distribution. It obeys what's called the generalized chi-squared distribution. It sort of looks Gaussian, but it's got a very heavy tail. And if you want to calculate your p-values correctly, p-values telling you the significance with which you can reject the null hypothesis, that there are no Hellions and Downs correlations present, then you need to know the statistics of that null distribution very well. And this is something that Lucas has been inspecting. Where'd Lucas go? Oh, there he is. Lucas has been digging into this recently as part of a project, and so can get that group going if they need to. There are probably people in the room, either in my group or more generally in the summer school, who have touched on various aspects of this. So I imagine there'll be at least one, maybe two people that are very close to each of these topics that can at least help the group get off the ground. If there's not a person in one of these groups that is familiar with how you would get going, then let us know and we can try to give some ideas. If none of these ideas appeal to you, if you've not signed up yet, that's fine. Just try to group together, find similar interests if you find other people that haven't signed up, and we can create a project that fits your interests. Is there anyone here who hasn't signed up to something in this list already? Perfect. Is everyone okay with exploring these kinds of ideas and with your group? There might be some people online that would like to get involved and talk with you all. Maybe the best thing would be to create your own mini project teams, like Slack teams, or just create a channel on our summer school Slack. And then eventually, as you're collecting together materials, maybe that's resources, maybe that's code that you want to share, probably create your own GitHub repositories and then share those around with each other. It would be nice if towards the end of hack sessions, we have some kind of summary and see where people are. So try to elect a representative who'll give a quick one-slide overview of where you are at the end of a hack session. And then we'll see where we are at the end of week one. And then on the very last day, teams will give a more extended summary of what project they were working on and the progress that they made. Again, this is very much for your benefit, so you can get some hands-on experience working with the concepts you're being introduced to. So it's not meant to be a high-pressure scenario. There's no expectation that you get all of this done, but it should be fun for you to try to explore some of those ideas. So the rest of today is choose your own adventure. I'd encourage you to get together with the teams that you've signed on with and start talking about your common interests, what kind of questions you'd like to answer within these areas, and start sketching out what you'll need to know, what code you might need, what packages you might need to download, and what are some concrete deliverables that you'd like to get to by the end of the 2 weeks. Do you want to get a certain plot? Do you want to get a certain number? How will you show what you actually want to show that will demonstrate, an answer to a question you want? Okay, so you can either stay in here. This room is always open. People familiar with the building, you can also go downstairs in the elevator, and there are multiple places to hang out and talk downstairs. There's a very open lounge area, and then if you go through the card access doors, which are always open until 5 p.m., you can get into what we call the living room area. It's got a kitchen in there. It's got a lounge, big TV to share screen. So up to you all. But I suggest you get together, you split off into your teams now and start discussions. Okay?
Yeah, I think